So, here's something worth thinking about as you settle in tonight. Right now, at this very moment, your body is slowly losing heat. You can feel it, maybe, at the tips of your fingers, or along the edge of your arm where the blanket doesn't quite reach. That warmth is leaving you. It's passing into the sheets, into the air, into the walls of the room around you. And you can't stop it. You can pile on more blankets, you can turn up the thermostat, but if you sit perfectly still and do nothing, your body will cool. The warmth flows away from you all on its own, quietly, steadily, without asking your permission. And here's the thing. For about 200 years, from roughly the middle of the 1700s to the early 1900s, the most brilliant scientists in Europe were absolutely convinced they knew what was happening. They believed that an invisible, weightless fluid was streaming out of your body. A fluid they called caloric.
They thought heat was a substance, a real physical thing, like water or air. Except you couldn't see it, couldn't weigh it, couldn't bottle it. It seeped between the tiny particles of matter, loosening them, making things expand, making things melt, making things boil. When something got cold, it simply meant the caloric had drained away, the way water drains from a bathtub. And the strangest part, the part that makes this story so much more interesting than a simple tale of smart people being wrong, is that this theory worked. It worked beautifully. It explained why hot things expand. It explained why ice absorbs heat when it melts without getting any warmer. It explained how steam engines function. It predicted the behavior of gases with remarkable precision.
The man who formalized the theory, Antoine Lavoisier, was arguably the greatest chemist who ever lived. And he was so confident in caloric that he placed it right there in his official table of chemical elements, alongside oxygen and hydrogen and nitrogen. Caloric was an element, as real as gold. And then, slowly, painfully, over the course of more than a century, this beautiful idea was torn apart. Not by one decisive experiment, not by one brilliant thinker having a single moment of clarity, but by a long, messy, emotionally brutal process in which the wrong answer kept defending itself, kept absorbing every blow, kept finding clever ways to explain away every contradiction, until finally, something better came along. Something so much more powerful, so much more beautiful, that the old idea simply couldn't compete anymore. That's the story I want to tell you tonight. The story of heat. What it is, how we figured it out, and why the wrong answer lasted so long.
Because this isn't just a story about science getting things right eventually. It's a story about what happens when an idea is so elegant, so intuitive, so deeply satisfying, that even the smartest people in the world can't bring themselves to let it go. It's a story about the difference between an answer that works and an answer that's true. And it has everything. Revolutions and guillotines, unlikely marriages and bitter separations, cannons and steam engines, obsessive experiments conducted in brewery cellars, a young soldier's humiliation in war, and a brilliant, tormented physicist who hanged himself while on holiday, while his wife and daughter were down at the beach. But it starts, as so many stories do, with a question so simple that a child might ask it. A question that turns out to be one of the hardest questions in all of science. What is heat? Just think about that for a moment. You know what heat feels like. You've felt the warmth of sunlight on your face, the sting of a hot pan, the gentle comfort of a warm bath. Heat is one of the most immediate, most visceral experiences a human being can have. Every living thing on this planet has some relationship with heat, from the bacteria in deep-sea vents to the lizard sunning itself on a rock. And yet, if someone asked you right now, lying there in the dark, to explain what heat actually is, not what it feels like, but what it is, what's actually happening when something is hot, you might find it surprisingly hard to give a clear answer. That difficulty isn't a sign that you haven't paid attention in school. That difficulty is real. It took humanity roughly 2,500 years to answer that question properly, and along the way, the wrong answer, that gorgeous, seductive, perfectly reasonable wrong answer, would fool some of the greatest minds in history. So here are the questions I want to sit with tonight.
What is heat really, at the deepest level? Why could brilliant people believe something completely wrong about it for 200 years? And what made the wrong answer so hard to let go of? And maybe the most unsettling question of all, if the smartest scientists who ever lived could be fooled by an elegant theory for 2 centuries, what does that say about the things you and I are sure we understand right now? How would you even know if the ideas you trust most are beautiful mistakes? Those are the questions, and the answers, when they come, will change the way you think about the warmth leaving your body right now, about the cup of tea cooling on your nightstand, about the fate of every star in the sky. But we'll get there slowly. Let's start where it actually started. Fire is almost certainly the first technology that humans ever mastered. Long before we built wheels or forged metal or planted seeds, we controlled fire.
Archaeological evidence suggests our ancestors were using fire in a deliberate, sustained way at least 400,000 years ago, and possibly much earlier. Fire cooked our food, which made nutrients more accessible and may have driven the expansion of our brains. Fire kept predators away at night. Fire let us survive in cold climates we never could have tolerated otherwise. And fire, sitting around it in the darkness, telling stories, sharing warmth, may have been one of the forces that shaped human social life itself. But for all our intimacy with fire, for all those hundreds of thousands of years of sitting beside it, feeding it, carrying it from camp to camp, we didn't understand it. We knew what fire did. We had no idea what fire was. And by extension, we had no idea what heat was either. Fire produced heat, obviously. But what was that heat? Where did it come from? Where did it go? Was it a thing? A substance? Something that existed inside the burning wood and was released when the wood was consumed? Or was it something else entirely? A process, an activity, something that happened rather than something that was? The ancient Greeks, who were the first people we know of to tackle these questions in a systematic way, had a range of ideas. Empedocles, writing around 450 years before Christ, proposed that everything in the world was composed of 4 fundamental elements: earth, water, air, and fire. In his picture, fire wasn't something that happened to matter. Fire was matter. It was one of the 4 basic ingredients of reality, woven into the fabric of every substance. When something burned, the fire element that had been trapped inside was simply being released. When something felt warm, it was because fire was present in it. When something felt cold, fire was absent. Aristotle, who came a century later and whose influence would dominate European thinking for nearly 2,000 years, took this further. He added a set of qualities to the elements. Fire was hot and dry. Water was cold and wet. Air was hot and wet. Earth was cold and dry. In Aristotle's scheme, heat wasn't so much a substance as a quality, a fundamental property that could be added to or removed from matter. You could, in principle, transform one element into another by changing its qualities. Heat water enough, change its cold quality to hot, and you'd get air. It was elegant, it was systematic, and it was wrong. but it was wrong in a way that felt deeply right. It matched everyday experience so well that it persisted, essentially unchallenged, for the better part of 2 millennia. Throughout the Middle Ages, across both the Islamic world and Christian Europe, scholars worked within variations of this Aristotelian framework. The alchemists who labored over their furnaces, trying to transmute base metals into gold, were operating under the assumption that heat was one of the fundamental qualities of matter, something you could add or subtract to change a substance's nature. They got incredibly good at practical chemistry, at distillation and extraction and purification, but they never questioned the basic framework. Heat was a quality. Fire was an element. That was the foundation, and nobody thought to dig beneath it. The first serious crack in this ancient picture appeared in the early 1600s, and it came from an unlikely source. Francis Bacon, the Lord Chancellor of England, a politician, essayist, and philosopher of science, was not a laboratory experimentalist in the way we'd understand the term today. But he was obsessed with methodology, with the idea that knowledge about nature should come from careful observation and experiment, rather than from the authority of ancient texts.
And in 1620, in a work called Novum Organum, Bacon turned his attention to heat. What Bacon did was remarkably systematic for his era. He made lists. He compiled a table of things that are hot: fire, sunlight, boiling water, animal bodies, fresh horse dung. He compiled a table of things that are cold: moonlight, air in winter, metal at room temperature. And then he compiled a third list, which was more subtle and more important. He listed situations where heat seemed to increase or decrease: friction, compression, vigorous exercise. And from these lists, he drew a conclusion that was, in its own quiet way, revolutionary. Heat, Bacon proposed, is not a substance and not a quality. Heat is a form of motion. Specifically, he wrote that heat is an expansive motion, restrained and striving to exert itself in the smaller particles of a body. The words are clumsy by modern standards, and Bacon's understanding of what he meant by particles was vague at best.
But the core idea is there. When something is hot, its tiny parts are moving. When something is cold, they're moving less. Heat, in Bacon's picture, was something that matter does, not something that matter has. Now, you might expect me to tell you that Bacon's insight was immediately recognized, that scientists picked it up and ran with it, and that the correct theory of heat was established in the 17th century. But that's not what happened. Not even close. Bacon's idea was noted, discussed, and then more or less set aside, for reasons that are actually quite understandable. The problem was that Bacon hadn't offered a mechanism. He'd said heat is motion, but he couldn't explain the details. What kind of motion? Motion of what, exactly? How did this motion produce the specific effects of heat, like melting, boiling, expansion? And crucially, how would you do any calculations with this idea? How would you predict anything? It was a philosophical claim, not a scientific theory.
It pointed in the right direction, but it didn't give anyone the tools to go anywhere with it. And yet, the idea didn't disappear entirely. About 40 years after Bacon, another Englishman picked up the thread. Robert Boyle was one of the wealthiest men in the British Isles, the son of the Earl of Cork, and he used his fortune to build an extensive private laboratory where he could pursue his scientific interests full-time. Boyle is most famous today for Boyle's law, the relationship between the pressure and volume of a gas that you might remember from school. But he was interested in everything, and one of the things that fascinated him most was cold. Boyle's longest published work, in fact, was a massive treatise on cold, called New Experiments and Observations Touching Cold. He carried out hundreds of experiments, trying to understand the nature of cold and, by implication, the nature of heat. And one experiment in particular is worth thinking about carefully. Boyle took a barrel of water and weighed it precisely. Then he put it outside in the snow and left it overnight to freeze. When the ice had formed, he weighed it again. The question he was asking was simple. If cold is a substance, some kind of fluid that flows into things as they cool, then the barrel should weigh more after freezing, because the cold substance has entered it. But the weight was exactly the same. No substance had flowed in. Boyle also noticed that the water had expanded as it froze, which raised another interesting point. If cold were a substance pushing its way between the particles of water, you'd expect the expansion. But if cold were simply the absence of heat, the slowing down of the water's particles, then the expansion might be explained by the particles arranging themselves into a more open structure as they lost their motion.
Boyle was becoming increasingly convinced that heat was a form of motion, that the tiny particles making up matter were jiggling and vibrating, and that temperature was a measure of how vigorously they moved. But here's what I find so revealing about Boyle's position. Even as he argued for the motion theory of heat, he admitted that he couldn't prove it conclusively. He complained, quite beautifully, that studying cold was like being a physician trying to work in a remote country without proper instruments or medicines. He could see what was happening, but he couldn't measure it properly, couldn't quantify it, couldn't build a mathematical framework around it. The tools simply weren't good enough. And this, as it turns out, was the crucial weakness. The motion theory of heat was a good philosophical idea. It pointed in the right direction. But it was vague, unmathematical, and practically useless for making predictions. And into that gap, into that space where the right idea couldn't prove itself, something else was about to grow. Something far more polished, far more quantitative, far more useful. Something that would seduce the entire scientific world for the next 200 years. The beautiful wrong answer was about to be born. But before we get to the beautiful wrong answer, there's an important detour I want to take. Because between Boyle's experiments in the late 1600s and Lavoisier's caloric theory in the late 1700s, something happened that changed the entire landscape of the question. Something practical, something enormous, something that would give the question of heat an urgency it had never had before. Machines appeared. Machines that ran on heat.
The story of how this happened involves a man named Gottfried Wilhelm Leibniz. And I want you to spend a moment with him, because he's one of those figures who makes you feel slightly inadequate about your own productivity. Leibniz was a diplomat, a mathematician, a philosopher, a historian, and a scientist. He co-invented calculus independently of Newton, which sparked one of the most vicious priority disputes in the history of science. He designed calculating machines. He corresponded with virtually every major intellectual in Europe. He was forever trying to understand the mechanisms that made the universe work. And one of the things that preoccupied Leibniz, starting around 1676, was a deceptively simple question. What happens when objects collide? When two billiard balls hit each other, the motion of one is transferred to the other. Something is being passed between them. Leibniz called this something the living force, vis viva. He thought of it as a real physical quantity, something almost tangible, a kind of invisible substance that got exchanged during collisions. He even argued that God had placed a fixed amount of living force into the universe at the moment of creation, and that this quantity was conserved, that it could never be created or destroyed, only transferred from one object to another. This might sound like a precursor to our modern concept of energy, and in many ways it was. Leibniz's living force was related to what we'd now call kinetic energy,
the energy of motion. He even had a formula for it, though he expressed it differently than we would today. And he saw something else, something that connected his abstract philosophical idea to the practical world of industry and power. Leibniz noticed that in gunpowder, in fire, in steam, his living force was being released in violent and powerful ways. If this release could be controlled, harnessed, directed, it could give human beings an almost godlike power over the natural world. The potential was staggering. Leibniz began corresponding with a young French scientist named Denis Papin about ways to capture and harness the living force of steam. Papin was enthusiastic. In a letter to Leibniz that has survived, he wrote with barely contained excitement about the possibilities. He claimed that through the power of steam, one man could do the work of 100. The machine, they imagined, a device that would convert the heat of burning fuel into mechanical motion, would augment the powers of man to infinity. Now, you might expect this to be the moment when the steam engine was invented and the world was transformed. But it wasn't. Leibniz and Papin were thinkers, not builders. Their ideas were profound and far-reaching, but they remained largely theoretical. For the steam engine to become real, you needed more than philosophy. You needed skilled craftsmen, innovative engineers, financial backers willing to take risks. You needed the practical, messy, trial and error world of industry. And that world existed, powerfully, in Britain. Over the course of the 18th century, British engineers, starting with Thomas Newcomen and culminating with James Watt, developed the steam engine from a crude, inefficient pump used to drain water from mines into a versatile, powerful machine that could drive factories, ships, and railways. By the early 1800s, steam engines were everywhere in Britain, and they were beginning to spread across Europe and America. The transformation was staggering. Steam replaced muscle, animal and human, with mechanical power that was, for practical purposes, limitless. Factories that had depended on water wheels, which only worked if you happened to be near a river, could now be built anywhere, powered by coal and steam. Ships that had depended on wind and sail could now cross oceans on a schedule, regardless of weather. Trains could haul goods and people across entire continents at speeds that would have seemed supernatural a century earlier. But here's what matters for our story about the nature of heat. These machines worked by converting heat into motion. Fire heated water. Water became steam. Steam expanded and pushed a piston. The piston turned a wheel. Heat went in at one end, mechanical work came out at the other. And nobody understood why. Let me emphasize that, because it's important. The steam engine was developed almost entirely through practical tinkering, through trial and error, through the accumulated skill and intuition of generations of engineers and mechanics. It was not developed from a theoretical understanding of how heat works. The theory came after the technology, not before. The machines existed, they ran, they transformed the world, and nobody could explain, at a fundamental level, what was happening inside them. This gap between practice and understanding is what gave the question of heat its urgency. As long as heat was a philosophical puzzle, it could wait. Clever people could debate whether heat was a substance or a form of motion, and nothing much rode on the answer. But once machines were converting heat into work on an industrial scale, the question became economic, even military. How efficient could these engines be? Were there fundamental limits? Could you build a perfect engine that converted all the heat into work with nothing wasted? Or was there some inescapable law of nature that set a ceiling on efficiency?
These were questions that mattered, that had real consequences measured in pounds of coal and horsepower and competitive advantage between nations. And they could not be answered without understanding what heat actually was. It was into this world of urgent, practical questions and deep theoretical confusion that two parallel developments emerged. One was a serious attempt to measure and quantify heat with precision, which would lead to the caloric theory. The other was the work of a humiliated young French soldier who would use the caloric theory to discover something so profound that even the death of caloric couldn't touch it. Let's take the measurement first. Before Joseph Black could discover latent heat, before Lavoisier could formalize the caloric theory, before anyone could do precise science with heat at all, there was a practical problem that had to be solved first. You needed to be able to measure temperature. And measuring temperature turned out to be a lot harder than you might think. The basic principle of a thermometer is simple. Most substances expand when they're heated and contract when they're cooled. If you put a liquid in a narrow glass tube, the level of the liquid will rise as the temperature goes up and fall as it goes down. People had understood this since at least the late 1500s. Galileo built a crude device called a thermoscope around 1600 that used the expansion of air to indicate temperature changes. But a thermoscope is not a thermometer. It shows you whether something is getting hotter or colder, but it doesn't give you a number. There's no scale. The problem of creating a useful temperature scale turns out to be surprisingly deep. You need fixed points, temperatures that are always the same, that you can use to calibrate your instrument. But which temperatures? In the early days, different instrument makers used different fixed points, and the resulting confusion was immense. One thermometer maker in Florence would use one set of reference temperatures. Another maker in London would use a completely different set, and their instruments couldn't be compared. A reading of 50 degrees on one thermometer might correspond to 30 degrees on another. The numbers were meaningless without a shared standard. The first person to create a widely adopted temperature scale was Daniel Gabriel Fahrenheit, a German-Dutch instrument maker working in the early 1700s. Fahrenheit was a craftsman of extraordinary skill, and his great innovation was the use of mercury instead of alcohol as the thermometric fluid. Mercury expands less than alcohol for a given temperature change, which means you need a finer tube, but it also means you can make the thermometer much smaller and more practical. Alcohol thermometers could be 6 or 8 feet long, sometimes wound into spirals to fit on a wall. Mercury thermometers were compact, portable, and much more useful in real-world settings, particularly for medicine, where you need to take a patient's temperature without inserting something the size of a broomstick. Fahrenheit chose 3 fixed points for his scale. His 0 was the temperature of a mixture of ice, water, and salt, which was the coldest stable temperature he could easily reproduce. His 32 degrees was the freezing point of pure water, and his 96 degrees was, somewhat oddly, the temperature of the human body, which he measured by placing his thermometer under his arm. The modern value of body temperature on the Fahrenheit scale is 98.6, which suggests either that Fahrenheit's thermometer was slightly off, or that his armpit was slightly cold. A few decades later, Anders Celsius, a Swedish astronomer, proposed a different approach. Celsius wanted a cleaner scale, one based on just 2 easily reproducible fixed points, the freezing and boiling points of water, with exactly 100 divisions between them. It was a beautifully logical system. But Celsius, for reasons that remain genuinely mysterious, put the scale upside down. In his original scheme, 0 was the boiling point of water and 100 was the freezing point. Hot was low and cold was high. Nobody knows why he did this. The most common guess is that he wanted to avoid negative temperatures, since most temperatures in Sweden are below the freezing point of water. But nobody's really sure. After Celsius died, the Swedish botanist Carl Linnaeus, who is much better known for inventing the system we use to classify living organisms, was president of the Swedish Academy of Sciences. Linnaeus looked at Celsius's upside-down scale and essentially said, "Enough of this nonsense." He flipped it. 0 became the freezing point. 100 became the boiling point. And the scale we now call Celsius has been that way ever since. So every time you read a temperature in Celsius, you're using a scale that was designed by an astronomer, inverted by a botanist, and named after the man who got it backward. This might seem like a digression, but it's actually central to our story. Because the development of reliable, standardized thermometers made it possible, for the first time, to do precise, quantitative experiments with heat. Without a good thermometer, you can observe that ice melts and water boils, but you can't measure how much heat is involved, how long the process takes, how temperature changes during the process. With Fahrenheit's and Celsius's thermometers, scientists could finally put numbers on thermal phenomena. And it was precisely this ability to measure that led Joseph Black to his discovery of latent heat and set the stage for the caloric theory. Because once you can measure temperature precisely, you notice things that are otherwise invisible. You notice, for instance, that a mixture of ice and water stays at exactly 32 degrees Fahrenheit, 0 Celsius, no matter how much heat you add, until all the ice has melted. That observation requires a thermometer. Without one, you just see ice melting and feel the water getting cold. With one, you can see that the temperature is doing something unexpected, staying perfectly constant while the ice absorbs heat. And that unexpected constancy is what Black noticed and what he called latent heat. So the thermometer made the caloric theory possible. Without precise measurement, Black couldn't have discovered latent heat. Without latent heat, the caloric theory wouldn't have had one of its strongest supporting pillars. The instrument enabled the theory, and the theory in turn guided further measurement. This feedback loop between measurement and theory is one of the engines of scientific progress, and it was running at full speed in the study of heat during the 18th century. To understand how the caloric theory came into being, you need to understand the problem it was designed to solve. And that problem was a genuinely puzzling one, the kind of thing that, if you think about it carefully, should bother you. Take a block of ice. Put it in a warm room. What happens? Obviously it melts. But watch carefully, and you'll notice something strange. As the ice melts, its temperature doesn't change. You can stick a thermometer in a glass of ice water, and as long as there's still ice in the glass, the temperature will sit stubbornly at 32 degrees Fahrenheit, and it won't budge. Heat is flowing into the ice from the warm room, clearly, because the ice is melting. But the temperature isn't going up. Where is that heat going? What is it doing? This was the puzzle that a Scottish chemist named Joseph Black tackled in the 1750s and 60s. and his answer would become one of the foundation stones of the caloric theory. Black was a professor at the University of Glasgow, a meticulous experimentalist with a talent for precise measurement. He was also, by several accounts, an exceptionally clear lecturer, the kind of teacher who could take a complicated idea and lay it out so that every student in the room understood it. And he needed that clarity, because the idea he was about to introduce was subtle. Black proposed that heat could exist in two forms. There was sensible heat, the kind you could feel and measure with a thermometer, the kind that makes things get hotter. And there was latent heat, from the Latin word for hidden. Latent heat was the heat that got absorbed by a substance when it changed state, when ice melted into water or when water boiled into steam, without any change in temperature.
The heat was still there, Black argued. It was just hidden. It had been absorbed by the substance and was now locked away inside it, doing the work of transforming solid into liquid or liquid into gas. Think about what this means. When you boil a kettle, the water sits at 212 degrees Fahrenheit, 100 Celsius, for as long as it takes to turn into steam. You're pouring energy into it the whole time, but the temperature stays flat. In Black's framework, all that energy is being absorbed as latent heat, used to break the bonds holding the water molecules together as liquid, converting them into the free-flying molecules of steam. And when that steam condenses back into water, that latent heat is released again, which is why a steam burn hurts so much more than a hot water burn. The steam dumps a huge amount of hidden energy into your skin as it condenses. Black's concept of latent heat was brilliant, and it was experimentally airtight.
He measured the quantities with great care. He could tell you exactly how much heat was needed to melt a given amount of ice, or to boil a given amount of water. These were real numbers, reproducible, reliable. And they cried out for an explanation. If heat was a form of motion, as Bacon and Boyle had suggested, then what did it mean for motion to be latent? How could motion be hidden? That's a very strange idea. Motion is motion. It's either happening or it's not. But if heat was a substance, a fluid, then latent heat made perfect intuitive sense. The fluid flowed into the ice. While the ice was melting, the fluid was being absorbed into the structure of the water, filling the spaces between the particles, loosening them, letting them slide over each other. The fluid was still there, hidden, stored away, doing structural work rather than raising the temperature. When the water froze again, the fluid was squeezed back out, released to flow into the surroundings. It was like water being absorbed by a sponge. The water doesn't disappear. It's just held in place and you can squeeze it back out later. This was incredibly elegant. It made latent heat comprehensible. And it was exactly the kind of quantitative predictive framework that the motion theory lacked. Black himself was cautious about committing fully to the substance theory of heat, but his experimental results were so naturally explained by it that the theory gained enormous momentum. And then Antoine Lavoisier arrived, and the beautiful wrong answer became official. Lavoisier is one of the towering figures of the history of science, and with good reason. Working in Paris in the 1770s and 80s, he essentially created modern chemistry. He identified oxygen's role in combustion, overthrowing the old phlogiston theory. He established the principle of conservation of mass in chemical reactions. He developed a systematic chemical nomenclature that we still use today, and he published the first modern chemistry textbook, the Traité élémentaire de chimie, in 1789. It was a masterwork, the foundation of a new science. And in that textbook, right there in the table of elements, alongside oxygen and hydrogen and nitrogen and carbon, Lavoisier listed caloric. He didn't hesitate. He didn't hedge. To Lavoisier, caloric was as real as any other element. It was an imponderable fluid, meaning it had no detectable weight, but it existed as a distinct substance. Every object in the universe contained a certain amount of caloric. When you heated something, caloric flowed into it. When it cooled, caloric flowed out. The particles of matter were surrounded by atmospheres of caloric, which repelled each other, and this repulsion was what made things expand when they were heated. The more caloric you added, the more the particles were pushed apart, and the substance expanded.
Lavoisier's wife, Marie-Anne Pauls, who was his scientific partner and illustrated many of his publications, assisted with the experiments that supported this theory. Together, they built a device called a calorimeter, an instrument for measuring the amount of caloric released or absorbed in various processes. The design was ingenious. The calorimeter had an outer compartment packed with ice. Inside that, there was a chamber where you could carry out chemical reactions or place living animals. The heat generated by the reaction or the animal would melt some of the ice, and by carefully collecting and weighing the meltwater, you could calculate exactly how much caloric had been released. Using this device, Lavoisier and his colleague Pierre-Simon Laplace measured the heat of combustion of various substances, the heat produced by animals during respiration, the heat involved in chemical reactions.
They showed that animal respiration was essentially a slow form of combustion, that the body burned food and released caloric in the same way that a candle burned wax. These were groundbreaking results, and they all fit perfectly within the caloric framework. Now, I want to take a moment to really appreciate how good the caloric theory was. Because it wasn't just a vague hand wave. It was a quantitative, predictive, experimentally supported theory that explained an enormous range of phenomena. Let me walk through some of what it could do. Why do things expand when heated? Because caloric flows in between the particles and pushes them apart. Simple, intuitive, correct in its predictions. Why does ice absorb heat when it melts without changing temperature? Because the caloric is being absorbed into the structure of the water, becoming latent, doing the work of separating the particles from their rigid arrangement. Black's data, perfectly explained.
Why does heat flow from hot objects to cold objects and never the other way around? Because caloric is a self-repelling fluid, and like any self-repelling fluid, it flows from regions of high concentration to regions of low concentration until it reaches equilibrium, just like water flowing downhill. Why do gases expand when heated and contract when cooled? Because adding caloric pushes the gas particles further apart, and removing it lets them settle closer together. This gave quantitative predictions that matched experiment. Why does friction generate heat? This was a slightly trickier one, and we'll come back to it because it turned out to be the theory's weak point. But the standard caloric answer was that friction squeezed caloric out of the material the way squeezing a sponge forces out water. The substance was already there, inside the metal or the wood. Friction simply liberated it. Do you see why this theory was so hard to abandon? It wasn't a fairy tale. It wasn't a lazy guess. It was a coherent, sophisticated, mathematically tractable framework that explained a vast range of experimental observations and made testable predictions that turned out to be correct. When you encounter a wrong theory that works this well, you start to understand something important about how science actually operates. Theories don't survive because they're true. They survive because they're useful. And caloric was phenomenally useful. Lavoisier himself would not live to see his theory challenged. In the early 1790s, the French Revolution consumed Paris. Lavoisier, who had been a tax collector for the Ancien Régime, was arrested. On May 8, 1794, at the age of 50, he was led to the guillotine and executed. There's a famous story, probably apocryphal, that the judge who sentenced him said, "The Republic has no need of scientists." It took less than a second to cut off a head that would have taken a century to produce, one of his colleagues wrote afterward. Lavoisier's papers, his instruments, his meticulous experimental records, all passed into the care of his widow, Marie-Anne. She would spend years editing and publishing his remaining work, fiercely guarding his scientific legacy. And that legacy included caloric. The beautiful wrong answer now had the weight of a martyr behind it. Lavoisier's chemistry was so revolutionary, so successful, that challenging any part of it felt almost like an act of disrespect. To question caloric was to question Lavoisier, and Lavoisier had been right about so many things. Now, before we get to the people who attacked this theory, I want to take a moment to paint the picture of what the caloric theory looked like in its full maturity. Because it really was a thing of beauty. Picture it as a complete system, a model of the physical world that explained heat in the same way that Newton's mechanics explained motion. It had principles, it had mathematics, it had predictions, and it had a community of brilliant scientists who worked within it and extended it. In the caloric picture, every material object in the universe was permeated by this invisible, weightless fluid. The caloric existed between the particles of matter, surrounding each particle in a kind of atmosphere, the way the air surrounds the Earth. These atmospheres of caloric repelled each other, which is why adding more caloric to a substance made it expand. The particles were being pushed further apart by the growing repulsion between their caloric atmospheres. Different substances had different capacities for caloric, what we now call specific heat capacities. Iron, for instance, had a low capacity for caloric, meaning that a small amount of caloric produced a large temperature change.
Water had a high capacity, meaning you had to add a lot of caloric to change its temperature significantly. These were measurable, reproducible quantities, and they were consistent with the caloric framework. If caloric was a fluid that flowed into materials, it made sense that different materials would have different capacities for absorbing it, just as different sponges absorb different amounts of water. The caloric theory also explained changes of state beautifully. When ice melted, caloric flowed into the ice and was absorbed, becoming latent. The caloric loosened the bonds between the ice particles, allowing them to move freely as liquid water. When the water boiled, even more caloric was absorbed, breaking the particles free entirely to become steam. The temperatures at which these transitions happened and the amount of caloric absorbed during each one were precisely measurable and perfectly consistent within the theory.
Heat conduction, the process by which heat flows through a solid material, like a metal rod, was explained as the flow of caloric through the spaces between particles, from regions of high caloric concentration to regions of low concentration. This was exactly analogous to the flow of water through a porous material, or the flow of an electric fluid through a conductor. The mathematics of heat conduction, developed most brilliantly by the French mathematician Joseph Fourier in his 1822 masterwork, The Analytical Theory of Heat, was entirely compatible with the caloric picture. Fourier's equations treated heat as a flowing quantity, and they worked spectacularly well, predicting the temperature distribution in heated objects with remarkable accuracy. Those equations, by the way, are still used today. They survived the death of caloric completely unchanged because they describe the behavior of heat flow correctly, regardless of what heat actually is. Even the behavior of gases fit neatly into the caloric framework. When you compress a gas, it gets hotter, Why? Because you're squeezing the caloric out of the spaces between the gas particles, concentrating it into a smaller volume, just as squeezing a wet sponge forces water out. When you let a gas expand, it cools. Why? Because the caloric is spreading out into a larger volume, becoming more dilute, just as water spreads thin when you pour it onto a wide surface. Scientists working within the caloric framework made important discoveries and developed powerful mathematical tools. Laplace used caloric theory to calculate the speed of sound in air, correcting an error in Newton's earlier calculation. Poisson derived equations for the expansion and compression of gases that are still taught in physics courses today, essentially unchanged. Carnot, as we'll see shortly, used caloric theory to analyze the fundamental operation of heat engines and derived results that remain valid 2 centuries later. The theory was productive. It generated research, guided experiments, inspired calculations, and produced correct predictions. It was, in the language of philosophers of science, a progressive research program. It wasn't stagnant. It was moving forward, producing new results, opening new lines of inquiry. Scientists working within it were not fools or dupes. They were doing first-rate science, guided by a framework that happened to be wrong about the underlying nature of heat, but right about enough of its behavior to be extremely useful. And this, I think, is the key lesson of the caloric story. A scientific theory can be wrong about fundamentals and still be right about details. It can be wrong about what heat is and still correctly predict how heat behaves. The behavior and the nature are different things. Caloric got the behavior right, in many cases, because the mathematical structures it used were appropriate for describing heat flow, regardless of whether the thing flowing was a substance or energy. The math didn't care. The equations worked. And that's precisely why caloric was so hard to kill. You can't easily abandon a theory that makes correct predictions. You can't easily let go of a framework that helps you solve real problems. The fact that caloric was wrong about fundamentals was, in a practical sense, almost irrelevant, as long as it kept working. And for a very long time, it did. But across the English Channel, a man with a truly extraordinary life story was about to take the first real swing at the beautiful lie. And his weapon of choice was a cannon. Benjamin Thompson was born in 1753 in Woburn, Massachusetts, in what was then the British colony of Massachusetts Bay. He grew up to be one of the most fascinating, most contradictory, and most irritating figures in the history of science. A man who managed to be a spy, a soldier, a bigamist, a government minister, a count of the Holy Roman Empire, a founder of one of the world's most important scientific institutions, and, eventually, the husband of Antoine Lavoisier's widow. His life reads like a picaresque novel written by someone who kept adding plot twists because they couldn't help themselves. Thompson was largely self-taught in science, but he was brilliant, ambitious, and utterly without scruples about which side he was on. During the American Revolution, he spied for the British. When the war ended, he was forced into exile, first to London, then to Bavaria, where he somehow managed to become a trusted advisor to the Elector, reorganizing the Bavarian army and designing social welfare programs.
For his services, he was made a Count of the Holy Roman Empire, and he chose the title Count Rumford, after the town in New Hampshire, now called Concord, where he had once lived. So the world knows him as Count Rumford, which sounds impressively aristocratic, but is actually just the name of a small New England town. Among Rumford's responsibilities in Bavaria was the oversight of the military arsenal, including the boring of cannon barrels. And it was here, in the 1790s, in a Munich artillery works, that he noticed something that would trouble the caloric theory at its core. Boring out a cannon barrel generates an enormous amount of heat. The friction between the drill bit and the metal is intense, and the barrel gets extremely hot. In the caloric framework, This was explained by saying that the friction squeezed caloric out of the metal, the way wringing out a cloth squeezes out water. The caloric had been there all along, stored in the metal.
Friction simply liberated it. Fine, reasonable enough. But Rumford started watching more carefully, and he noticed something that didn't fit. The amount of heat produced seemed to be inexhaustible. He could keep boring, and the metal just kept getting hotter. Hour after hour, the heat kept coming. If caloric were a substance stored inside the metal, you'd expect the supply to run out eventually. You can only squeeze so much water from a cloth. But the heat never stopped. As long as the boring continued, heat was produced, without any apparent limit. Rumford decided to put this to a proper test. He designed a deliberately inefficient boring setup, using a blunt bore that would produce maximum friction and minimum actual cutting. He enclosed the cannon barrel in a wooden box and filled the box with water. Then he set the horses turning the bore and waited. After about 2.5 hours, the water boiled. Let me say that again, because it's a remarkable thing. He started with a cannon barrel immersed in cold water, and through nothing but mechanical friction, with no fire, no combustion, no chemical reaction of any kind, he boiled the water. The heat just kept coming, continuously, as long as the horses kept turning. Rumford was exultant. He published his results in 1798 in a paper presented to the Royal Society of London, and his argument was forceful. The amount of heat produced by friction, he wrote, appeared to be inexhaustible. And anything that can be produced without limit, he reasoned, cannot be a substance. No material object can be created from nothing in unlimited quantities. Therefore, heat cannot be a substance. Heat must be a form of motion. It's a compelling argument, and reading it today, with the benefit of hindsight, it seems like it should have been decisive.
Rumford had shown, experimentally, that heat could be generated from mechanical work alone, in unlimited quantities, with no chemical change, no combustion, no apparent source of caloric. Surely this killed the caloric theory dead. But it didn't, and the reasons it didn't are themselves a fascinating part of the story. First, Rumford's experiment, while dramatic, wasn't actually as airtight as he believed. The caloric theorists had a counter-argument. They pointed out that the metal shavings produced during boring had a lower heat capacity than solid metal. This meant that the same amount of caloric distributed among the shavings would produce a higher temperature. In other words, the caloric was already there, in the metal. The boring process just rearranged it, concentrating it in a smaller volume of shavings, making those shavings hotter. The total amount of caloric was conserved.
Rumford had anticipated this objection, and he'd tried to address it by using a blunt bore that produced very few shavings. But his experiment was messy, hard to quantify precisely, and the caloric theorists could always argue that subtle effects were being overlooked. The experiment was suggestive, not conclusive. Second, and this is the deeper point, Rumford was offering only a negative argument. He was saying what heat wasn't. He wasn't providing a better theory, he had no mathematical framework, he had no quantitative predictions. He was saying that caloric was wrong. But he wasn't offering anything to replace it with. And in science, as in life, you can't beat something with nothing. A working theory, even a flawed one, will survive as long as there's nothing better available to take its place. The caloric theory, for all its problems with Rumford's canon, was still a functioning quantitative framework that scientists used every day to analyze heat flow, to design experiments, to understand chemical reactions. Rumford's motion theory was a philosophical claim backed by one admittedly impressive but somewhat ambiguous experiment. It wasn't enough. And so the caloric theory absorbed the blow, adjusted its explanation slightly, and carried on. Rumford, frustrated, eventually left science and moved to Paris, where his personal life took a turn that you truly couldn't make up. Remember Marie-Anne Paulze Lavoisier, the widow of Antoine Lavoisier, the man who had made caloric an element? She was brilliant, wealthy, well-connected, and deeply devoted to preserving her late husband's scientific legacy. Rumford, the man who had tried harder than anyone else to destroy that legacy, met her in Paris in the early 1800s. And in 1805, they got married. It was a disaster. By all accounts, they made each other miserable from almost the first day. Rumford complained that Marie-Anne was extravagant and hosted too many dinner parties. Marie-Anne complained that Rumford was controlling and poured boiling water on her flowers. They separated after less than a year. Rumford reportedly told a friend that Lavoisier had been lucky to have been guillotined. It's a wickedly ironic detail, and it's tempting to dwell on it, but what matters for our story is what happened to the science. Rumford's cannon experiment had landed a blow against caloric, but the theory had survived. It was bruised, maybe, slightly less confident, but still dominant, still useful, still the working framework that scientists use to think about heat. The wrong answer was still standing. And then something happened that would change everything. Not another philosophical argument, not another single experiment.
Something much bigger, much more powerful, much harder to ignore. Machines. Enormous, thundering, smoke-belching machines that were transforming the face of the Earth. Machines that ran on heat, that converted heat into motion, that turned fire into work. Machines that demanded to be understood, not for philosophical reasons, but for intensely practical ones. The age of steam had arrived, and within the noise and fury of those engines, buried inside their pistons and cylinders and boilers, a young French soldier was about to discover a truth so profound that neither he nor anyone else at the time would fully grasp what he'd found. By the early 1800s, the steam engine had become the most important technology on Earth. Not important in the way that a clever gadget is important in the way that agriculture is important, or language, or fire itself. Steam engines were draining mines, powering factories, driving ships, hauling goods across entire continents. They were the beating heart of the Industrial Revolution. And the country that had mastered them most completely was Britain. If you wanted a single image to capture the sheer ambition of the steam age, you might look at a place like Crossness in southeast London, built in 1865, where 4 enormous steam engines with 47-ton beams each consumed 5,000 tons of coal per year. And the purpose of these magnificent machines, housed in a building decorated with the kind of ornate ironwork you'd expect on a luxury ocean liner, was to pump sewage. That's how central steam had become to daily life. Even the sewage got a cathedral. But for all their power and grandeur, steam engines were deeply mysterious. Engineers had gotten remarkably good at building them, through decades of trial and error and practical tinkering. They could make them bigger, make them more reliable, make them produce more power. But almost nobody understood, at a fundamental level, why they worked. What was actually happening inside the engine? What was the relationship between the heat going in and the work coming out? Was there a limit to how efficient they could be? Was there some ceiling that no amount of clever engineering could break through? These weren't academic questions. They were economic questions. Coal was expensive. Every bit of heat that was wasted, that went up the chimney or radiated from the boiler without doing useful work, was money lost. If you could understand the fundamental principles governing the conversion of heat into work,
you could build better engines, save fuel, and gain an enormous competitive advantage. And this is where the story of Nicolas Léonard Sadi Carnot begins. And to understand why this young man attacked the problem with such fierce determination, you need to understand the humiliation that drove him.
Carnot was born in 1796 into one of France's most prominent military families. His father, Lazare Carnot, was known as the organizer of victory for his role in leading the French revolutionary armies. Sadi himself attended the prestigious École Polytechnique in Paris, one of the best engineering schools in the world, and trained as a military engineer. He was brilliant, serious, and deeply patriotic. And then, in 1814, Paris fell. During the final campaigns of the Napoleonic Wars, with Napoleon and most of the French army fighting elsewhere, a coalition of Russian, Prussian, and Austrian forces advanced on Paris itself. The defense of the city fell partly to students and cadets, including those from the École Polytechnique. Young Carnot was among them, fighting at the Château de Vincennes on the outskirts of Paris. The defense failed. The students, inexperienced and outgunned, were forced to retreat under sustained artillery fire. Paris was taken.
Napoleon abdicated. France was humiliated. For Carnot, this wasn't just a national defeat. It was personal. He had stood on the walls of Vincennes and watched his country's enemies pour through the defences. And in the aftermath, as he tried to understand why France had lost, one factor stood out above all others. Britain's mastery of steam technology had given it an overwhelming economic and military advantage. British factories outproduced French ones. British ships outgunned French ones. British industry was powered by steam in a way that French industry simply was not. Carnot wrote explicitly that if you could take steam engines away from Britain, the British Empire would collapse. He was convinced that understanding steam was not just a scientific problem, but a matter of national survival. And so, living on half pay as a demobilized officer, sharing a small apartment in Paris with his brother Hippolyte, he set out to do something that no one had properly done before.
He set out to understand the fundamental principles governing how heat engines work. The result was a slim book published in 1824, just 118 pages long, in a print run of only 600 copies. It was called Reflections on the Motive Power of Fire, and it is one of the most important scientific works ever written. Here is what makes Carnot's achievement so remarkable, and so relevant to our story about the caloric theory. Carnot used the caloric theory to analyze heat engines. He believed, as almost everyone did at the time, that heat was a substance, a fluid that flowed from hot to cold. And he used that framework to build his entire analysis. And the analysis worked. Carnot's central insight was based on an analogy with water wheels. A water wheel extracts useful work from falling water. The water doesn't get used up. It flows from a higher reservoir to a lower one, and as it falls, it turns the wheel.
The work you can extract depends on two things: the amount of water and the height of the fall. Carnot proposed that heat engines work the same way. Heat, which he conceived as caloric, flows from a hot reservoir, the furnace or boiler, to a cold reservoir, the condenser or the open air. As it flows, the engine extracts useful work. The heat doesn't get used up, just as the water doesn't get used up in a water wheel. It simply falls from a higher temperature to a lower one. And the crucial insight was this: the amount of work you can extract depends on the temperature difference. A bigger drop in temperature means more work, just as a higher waterfall means more power from a water wheel. If you want to make your engine more efficient, you need to maximize the temperature difference between the hot source and the cold sink. Run your furnace as hot as possible and your condenser as cold as possible, and you'll get the most work out of every unit of heat. This insight has guided engineers for 200 years. It's the reason a car engine, which operates at higher temperatures than a steam engine, is more thermally efficient. It's the reason jet engines, which run at even higher temperatures, are more efficient still. It's one of the most practically important ideas in the history of engineering. But here's the thing that makes Carnot's story so fascinating from the perspective of our tale about caloric. Carnot's analysis was built on a wrong foundation. He believed heat was a conserved fluid that flowed without being consumed. In reality, heat is not conserved in an engine. Some of the heat is actually converted into work. The heat that enters the engine at the hot end is greater than the heat that leaves at the cold end, because some of it has been transformed into mechanical energy. And yet, despite being built on a wrong assumption, Carnot's conclusions about efficiency were correct. The maximum efficiency of a heat engine really does depend on the temperature difference between the hot and cold reservoirs. The formula still stands. The predictions still hold. The wrong theory gave the right answer. Think about what that means. Carnot used caloric, a theory that was fundamentally incorrect about the nature of heat, and produced results that are still taught in every engineering course in the world today. The theory was wrong, but the conclusions were right. How is that possible? The answer, which wouldn't be fully understood until later, is that Carnot's reasoning captured something real about the behavior of heat, something that was true regardless of whether heat was a substance or a form of motion. The directionality of heat flow, the fact that it naturally moves from hot to cold and not the other way around, the relationship between temperature difference and the ability to extract work. All of this is real physics.
Carnot happened to reach these truths through a framework that was wrong about the underlying mechanism. But the truths themselves were robust. They survived the death of the theory that gave birth to them. Carnot himself may have begun to suspect that his framework was flawed. After his death, notes were found in his papers suggesting that he was moving toward the idea that heat and work were interconvertible, that heat wasn't conserved in an engine, but was actually used up, transformed into motion. If he'd lived longer, he might have made this leap himself, but he didn't live longer. In the summer of 1832, a devastating cholera epidemic swept through Paris. The disease was poorly understood, terrifying, and almost invariably fatal once symptoms appeared. Carnot, brave and scientifically curious, decided to study the epidemic, to observe and document its spread. He went into hospitals, visited the sick, tried to understand the pattern of contagion, and he caught it.
On August 24th, 1832, Sadi Carnot died of cholera. He was 36 years old. Because cholera was so feared, and because nobody understood how it spread, many of Carnot's personal possessions and papers were burned to prevent contagion. We don't know how much of his thinking was lost in those flames. The slim book, The Reflections, survived. But it sat in near total obscurity for years. Only 600 copies had been printed, and almost nobody read it. The ideas that would eventually reshape our understanding of the universe gathered dust on the shelves of a few Parisian bookshops. Carnot had glimpsed something profound. He had shown that there was a deep relationship between heat, temperature, and the ability to do work. He had laid the foundation for an entirely new science. But his foundation was built on caloric, and caloric was a lie. The question now was, could anyone see past the lie to the truth beneath it? Could anyone separate what Carnot had gotten right from what he'd gotten wrong? And what would happen when they did? The answer would come from two very different places at almost the same time: a quiet brewery in Manchester, England, and a lecture hall in Berlin, Germany. And together, the discoveries made in these two places would bury the caloric theory forever. though not before it put up one last magnificent fight. I want to stay with Carnot for a moment longer, because there are details of his story that deserve to be told more slowly. After the fall of Paris in 1814, Carnot found himself in the strange limbo that befalls soldiers when the war ends and they are no longer needed. He was placed on half pay, which was barely enough to live on, and he shared a small apartment with his brother Hippolyte. He had no laboratory, no institutional affiliation, no research funding.
He was a military engineer without a war to fight, living in a city that was still reeling from defeat and occupation. And yet, this period of enforced idleness turned out to be extraordinarily productive. Freed from the demands of military service, Carnot threw himself into the study of heat engines with an intensity that bordered on obsession. He visited factories. He studied the designs of every type of engine he could find. He read everything that had been written about steam power, which wasn't much at the time. And he thought. He thought with the kind of sustained, focused intensity that only comes when you have nothing else to do and nothing to lose. What Carnot was looking for was not a better engine design. He wasn't an engineer trying to improve a specific machine. He was a theorist trying to understand the general principle behind all machines. He wanted to know, what is the maximum possible efficiency of any heat engine? Not this engine or that engine, but any engine, the ideal engine, the perfect engine that no real engine could ever surpass. This was an extraordinarily ambitious question, and the fact that Carnot answered it at the age of 28, working alone with minimal resources, using a theoretical framework that turned out to be wrong about the fundamental nature of heat, is one of the most impressive intellectual achievements of the 19th century. Carnot's method was to imagine an ideal engine, one that operated with perfect efficiency, with no friction, no heat loss, no waste of any kind. This imaginary engine, now called the Carnot cycle, goes through a specific sequence of steps. It absorbs heat from a hot reservoir, does work by expanding, dumps the remaining heat into a cold reservoir, and then is compressed back to its starting state, ready to begin again.
Carnot showed that the efficiency of this ideal cycle depends only on the temperatures of the hot and cold reservoirs. Nothing else matters, not the working fluid, whether it's steam or air or anything else. Not the size of the engine, not the speed at which it operates, only the temperatures. And the greater the difference between hot and cold, the higher the efficiency. He also showed something even more profound. No real engine can ever be more efficient than the Carnot cycle operating between the same temperatures. Any real engine, with its friction and its heat losses and its imperfections, will always fall short of the ideal. This is an absolute ceiling, set by the laws of nature, that no amount of clever engineering can break through. Now, Carnot derived all of this using the caloric theory, believing that heat was a conserved fluid flowing from hot to cold. But the result is correct.
The maximum efficiency formula is the same whether you think of heat as a substance or as energy. The truth, Carnot found, was deeper than the framework he used to find it. And there's a poignant footnote to this. Among Carnot's papers, found after his death, were notes that suggest he was beginning to doubt the caloric theory. He jotted down calculations showing that heat could be converted into work, that the heat entering an engine was not entirely conserved, but was partly consumed. He was, it seems, on the verge of discovering the first law of thermodynamics, the conservation of energy, all on his own. He may have realized that his own theory was built on a flawed foundation. But cholera took him before he could follow this thread to its conclusion. his notes were burned with his other possessions, and the world had to wait another 20 years for Joule and Thomson and Clausius to put the pieces together. Carnot's book, The Reflections, gathered dust for nearly 2 decades.
When William Thomson finally tracked down a copy in Paris, he was astonished by what he found. Here was a complete analysis of the fundamental principles of heat engines, written by a man who had died young and been almost entirely forgotten. Thomson brought Carnot's ideas back into the scientific mainstream, and they became one of the twin pillars of thermodynamics, alongside Joule's discovery of the mechanical equivalent of heat. The irony is almost too perfect. The caloric theory, the beautiful wrong answer, had produced through Carnot one of the most important and enduring results in the history of physics. The wrong theory had given birth to a truth that would outlive it. In the 1840s, a young Scottish physicist named William Thomson, who would later become Lord Kelvin, one of the most important figures in the history of thermodynamics, went hunting for a book. He was in Paris, and he wanted to find a copy of Carnot's Reflections on the Motive Power of Fire. He knew the book existed. He knew it contained important ideas, but he couldn't find it anywhere. He searched the bookshops of Paris. He wandered the stalls along the banks of the Seine. He asked booksellers, and they told him they'd never even heard of it. Eventually, somehow, he got his hands on a copy, and what he read electrified him. Carnot's analysis of heat engines was clearly profound. The idea that there was a fundamental limit to the efficiency of an engine determined by the temperature difference between hot and cold was powerful and new. But Thomson also sensed that something wasn't quite right. Carnot had assumed that heat was conserved, that it flowed through an engine without being consumed. And Thomson was hearing about new results from England that suggested otherwise. Those results came from James Prescott Joule. And to understand Joule, you need to understand Manchester. Manchester in the 1840s was the throbbing heart of the Industrial Revolution.
Cotton mills, iron foundries, chemical works, all powered by steam, all consuming coal at a prodigious rate. The air was thick with soot. The rivers ran dark with industrial waste. And everywhere, the question of efficiency hung in the air like the smoke itself. How much useful work could you extract from a given amount of coal? How much was being wasted? Every factory owner in Manchester thought about this, because coal cost money, and wasted heat was wasted profit. James Joule was born in 1818 into a family of brewers. The Joule family ran a successful brewery in Salford, just outside Manchester, and James would eventually take over the business. But from an early age, he was far more interested in science than in beer. He had been tutored privately by John Dalton, the great chemist and originator of modern atomic theory, who happened to live in Manchester.
Dalton instilled in the young Joule a love of precise measurement and a conviction that the laws of nature could be expressed in exact numbers. Joule was not a university professor. He never held an academic position. He was a gentleman amateur, working in a laboratory he'd set up in his family's brewery, using thermometers of extraordinary precision that happened to be available because brewers needed to monitor temperature during fermentation. This turns out to be a detail that actually matters. Joule's thermometers could detect temperature changes of a fraction of a degree, far more precisely than the instruments available to most academic physicists at the time, and that precision would prove essential. Because the experiment Joule was about to conduct would produce only a tiny, tiny temperature change, one that most instruments would have missed completely. Here's what Joule did. He built an apparatus consisting of a paddle wheel inside an insulated container of water. The paddle was connected by a string over a pulley to a pair of falling weights. When the weights fell, they turned the paddle, which churned the water. The friction of the paddle against the water generated heat. The setup was, in a sense, the reverse of a steam engine. A steam engine takes heat and converts it into mechanical motion. Joule's apparatus took mechanical motion, the falling of the weights, and converted it into heat. If heat was truly a substance, caloric, then this shouldn't have been possible. Where was the caloric coming from? The weights didn't contain caloric. The pulley didn't contain caloric. The paddle didn't contain caloric. And yet, heat was appearing in the water. Joule measured everything with painstaking care. He measured the height from which the weights fell, which told him precisely how much mechanical energy was being supplied. He measured the temperature of the water before and after, using his brewery thermometers that could detect fractions of a degree. And he calculated the ratio. How much mechanical energy did it take to raise the temperature of a given amount of water by 1 degree? He ran the experiment over and over, with different setups, different amounts of water, different weights, different heights. And every time, he got the same ratio. A specific, constant, reproducible amount of mechanical energy always produced the same amount of heat. It didn't matter how you generated the friction. It didn't matter what materials you used. The conversion factor was universal and fixed. This result, which we now call the mechanical equivalent of heat, was devastating for the caloric theory. Because it showed that heat and mechanical energy were interconvertible. A specific amount of one always produced a specific amount of the other. They weren't different substances.
They weren't fundamentally different things. They were different forms of the same underlying quantity, what would eventually be called energy. Joule himself put it beautifully. He measured that the amount of mechanical energy needed to raise 1 pound of water by 1 degree Fahrenheit was equivalent to a weight of 772 pounds, falling 1 foot. Modern measurements put the number at 778, so Joule was remarkably close, especially given the sensitivity of the measurement. And here's a lovely detail about Joule that I don't want you to miss. There's a famous story, possibly apocryphal but widely told, that Joule spent part of his honeymoon in the Swiss Alps trying to measure the temperature difference between the top and bottom of a waterfall. His reasoning was simple. If the water falls from a height, it has mechanical energy. When it hits the pool at the bottom, that energy is converted into heat.
So the water at the bottom should be very slightly warmer than the water at the top. He reportedly brought thermometers on his honeymoon and spent time at waterfalls trying to detect this tiny temperature difference while his new wife presumably waited nearby with varying degrees of patience. Whether or not the story is exactly true, it captures something essential about Joule. He was obsessed with precision, obsessed with the idea that the conversion between heat and work was a fundamental law of nature, and he was willing to go to extraordinary lengths to prove it. And what he proved, ultimately, was that heat is not a substance. You can create heat from mechanical work in exact proportion with perfect reproducibility. There is no caloric fluid being squeezed out or released or transferred. The heat is created from the mechanical energy itself. They are two forms of the same thing. This idea, formalized and generalized, became the first law of thermodynamics.
Energy can be converted from one form to another, but the total amount of energy in any isolated system remains constant. Energy is conserved. It is never created or destroyed. It just changes form. Heat can become work. Work can become heat. Chemical energy can become heat. Heat can drive chemical reactions. light can become heat. And in every conversion, the books always balance. What goes in equals what comes out. The first law was a triumph. It unified an enormous range of phenomena under a single principle, and it drove the final nail into the coffin of caloric as a conserved substance, because in a steam engine, heat is not conserved. It's partly converted into work. The heat that comes out of the engine's cold side is less than the heat that went in at the hot side, and the difference is the work performed by the engine. Carnot's waterfall analogy was wrong in its details. Heat doesn't flow through an engine the way water flows over a wheel, unchanged and conserved.
Some of the heat is consumed, transformed, turned into motion. But here's the delicious irony. Even as Joule's work destroyed the caloric theory's claim that heat was a conserved substance, it also vindicated Carnot's deeper insight. Because the first law by itself doesn't explain why engines work in one direction. It doesn't explain why heat flows from hot to cold and not the other way around. It doesn't explain why you can easily convert work into heat. Just rub your hands together. But converting heat back into work requires an elaborate engine and is never fully efficient. The first law says energy is conserved. It doesn't say anything about which way it likes to go. For that, you need the second law. And the second law would take the caloric theory's last remaining strength, its beautiful explanation of the directionality of heat flow, and turn it into something far stranger and more profound. The man who would take this next step was a young German physicist, and he was about to introduce the world to a concept so deep, so mysterious and so universal that we're still arguing about what it really means. Let me tell you a bit more about Joule's personality, because it matters for understanding why his results were initially ignored and why they eventually prevailed. Joule was not a charismatic speaker. He wasn't a brilliant lecturer. He wasn't a powerful figure in the academic establishment. He was a brewer from Manchester, a city that the London-based scientific elite tended to view with a certain condescension, as a place of commerce and industry rather than pure learning. When Joule presented his results, he did so in a flat, methodical style that was heavy on numbers and light on drama. He was the kind of scientist who let the data speak for itself, which is admirable in principle, but often ineffective in practice, because data doesn't actually speak. It needs an advocate. At that first presentation in 1843 at the British Association meeting in Cork, Joule was essentially brushed off. The audience was polite but uninterested. His paper was too long, his manner too dry, his claims too radical. He was saying that heat and mechanical work were fundamentally the same thing, that they could be converted into each other in fixed proportions. This was a direct assault on the caloric theory, and it was coming from a brewer with no university appointment. But Joule was persistent to the point of stubbornness. He kept measuring. He kept refining his experiments. He tried different methods of generating heat from mechanical work, not just paddle wheels in water, but also compressing air, forcing water through narrow tubes, and running electrical current through resistors. In every case, he found the same fixed conversion ratio between mechanical energy and heat. The ratio didn't change with the method, the material, or the conditions. It was a universal constant. By 1847, Joule was presenting his results again, this time at the British Association meeting in Oxford. Once again, the reception was cool, and the chairman suggested he keep it brief. But this time, someone in the audience was paying close attention.
a young man stood up and asked a series of incisive, probing questions about the implications of Joule's measurements. That young man was William Thomson, the future Lord Kelvin, and this encounter would prove to be a turning point. Thomson was deeply interested in Carnot's work on heat engines, which he had recently read for the first time. Carnot's analysis assumed that heat was conserved, that it flowed through an engine without being consumed. But Joule's experiments seemed to show the opposite, that heat could be created from mechanical work, which meant it wasn't conserved at all. These two results appeared to contradict each other. Both couldn't be right. And yet, Thomson realized with growing excitement, maybe they could. Maybe both Carnot and Joule were right, in a sense, about different aspects of the same deeper truth. Carnot was right that the efficiency of an engine depends on the temperature difference. Joule was right that heat and work are interconvertible. The contradiction was only apparent. It arose from the false assumption that heat was a substance. Remove that assumption, replace it with the idea that heat is a form of energy, and both Carnot's efficiency theorem and Joule's conversion experiments fell into place as parts of a single, unified framework. Working out the details of this synthesis took several years and involved contributions from Thomson, Clausius, and others. But the essential insight, the moment when the pieces clicked into place, can be traced back to that meeting in Oxford, when a young Scottish physicist listened carefully to a Manchester brewer and realized that the old theory of heat, for all its beauty and usefulness, was fundamentally wrong. Joule had done something that Rumford's Cannon experiment hadn't quite managed. He had produced a quantitative result, a precise number that was reproducible and universal, and that the caloric theory simply could not explain away. You can argue about whether cannon boring generates heat from friction or from changes in heat capacity. You can't argue with a universal conversion constant. The number spoke, and it said, heat is energy. Joule spent the rest of his life refining his measurements and extending his results. He never became a major academic figure. He never held a professorship. He continued running the family brewery and doing science on the side. But his contribution was recognized, eventually. The unit of energy in the International System of Units, the Joule, is named after him. Every time you see an energy value on a food label or in a physics textbook, expressed in joules or kilojoules, you're using the name of a quiet brewer from Manchester who had very good thermometers and the patience to use them. Rudolf Clausius was born in 1822 in Köslin, in the Prussian province of Pomerania, a region that now lies in modern Poland. He was, by all accounts, a brilliant and serious young man, the kind of student who caught the attention of his professors early and moved through the academic ranks with a speed that would be unusual in any era. By his late 20s, he was already a professor in Berlin, and within a few years he would move to the newly established Polytechnic in Zurich, Switzerland, where he would do some of his most important work. Clausius was not a flashy personality. He didn't have Rumford's colourful biography or Joule's charming obsessiveness. He was a mathematician at heart, a man who expressed his deepest insights in equations rather than anecdotes. But what he lacked in personal drama, he more than made up for in intellectual clarity. Because Clausius saw something that no one else had seen quite so plainly, something that seems obvious once you hear it, but that turns out to have staggering implications. He saw that heat has a direction. Now, at first, that sounds like the most trivial observation in the world. Of course, heat has a direction. Everyone knows that hot things cool down. Everyone knows that if you put an ice cube in a warm drink, the ice melts and the drink gets cooler, not the other way around. Your hot cup of tea, sitting on the nightstand, will always cool down to room temperature. It will never spontaneously get hotter while the room gets colder. You know this from a lifetime of experience. It seems like the most obvious thing in the world.
But Clausius was the person who looked at this completely ordinary, everyday observation and thought what no one else had thought. He turned it into a law of physics. As Clausius put it, heat cannot of itself pass from a colder to a hotter body. That's it. That's the whole thing. 13 words that would reshape our understanding of the universe. Let me explain why this is so much more profound than it appears. The first law of thermodynamics says energy is conserved. It doesn't say what energy is allowed to do. As far as the first law is concerned, there's nothing wrong with heat flowing from a cold object to a hot one. The books would still balance. Energy would still be conserved. A cold drink sitting on your table could, in principle, transfer heat to the warm air around it, getting even colder while the air gets even warmer. That wouldn't violate conservation of energy. The total energy in the system would remain the same.
But it never happens. Not once. In the entire history of the universe, has a cup of cold water spontaneously gotten colder while the surrounding air got warmer. The process goes one way. Always. Without exception, heat flows from hot to cold and never, ever the other way around, unless you do something to force it. Unless you spend energy to make it happen. Like a refrigerator does. Clausius realized that this wasn't just an observation, it was a fundamental law of nature, as deep and as universal as the conservation of energy itself. And he spent the better part of 2 decades developing the mathematical framework to express it precisely. The result was the second law of thermodynamics, and it introduced a new quantity that Clausius named entropy, a word he deliberately coined from the Greek word for transformation. Now, entropy is one of those concepts that has a reputation for being deeply confusing. And part of the reason is that Clausius himself defined it in a very mathematical, very abstract way that's hard to translate into plain language. But let me try, because it's worth understanding, at least at the level of feeling, what entropy is about. Clausius showed that whenever heat flows from a hot object to a cold object, something happens that can't be undone. The heat disperses, it spreads out. It goes from being concentrated in one place to being spread over a larger volume. And this spreading, this dispersal, is entropy increasing. Here's a concrete example. Imagine you have a hot mug of tea sitting on a table. The tea is at about 175 degrees Fahrenheit. The room is at around 68. Over time, the tea cools down and the room warms up, very slightly. Eventually, everything reaches the same temperature, maybe 69 degrees or so. The total energy in the system hasn't changed. The heat that left the tea went into the room. First law satisfied. But something has changed. The energy is now more evenly spread out. It was concentrated in the tea, in a small volume, at high temperature. Now it's dispersed across the entire room, at a low temperature. And you can't get it back. You can't unstir the heat out of the room air and reconcentrate it into the mug. That process is irreversible. And the quantity that measures this irreversibility, this spreading out, this loss of concentration, is entropy. Clausius's great equation says that when heat Q flows from a body at temperature T, the entropy change is Q divided by T. And since heat always flows from hot to cold, from high T to low T, the entropy increase on the cold side is always greater than the entropy decrease on the hot side. So the total entropy of the system always goes up. Always. In every process. Without exception, as long as the process involves heat flow. Clausius was so confident in his mathematics, so certain that this principle applied universally, that he made 2 sweeping pronouncements about the cosmos. The first,
The energy of the universe is constant. That's the first law. The second, the entropy of the universe tends toward a maximum. That's the second law. Think about what that second statement means. If entropy is always increasing, if the universe is always dispersing its energy, spreading it out more and more evenly, then eventually, far in the future, everything will reach the same temperature. Every star will have burned out, every hot region will have cooled, every cold region will have warmed. The universe will be a vast, uniform, lukewarm bath with no temperature differences anywhere. And with no temperature differences, no engine can run, no work can be done, no life can exist, nothing can happen.
This idea became known as the heat death of the universe, and it was one of the most disturbing ideas of the 19th century. The universe, according to the second law, is winding down. It's running out, not of energy. Energy is conserved, but of usable energy, of concentrated energy, of the temperature differences that make work and life and everything we care about possible. Now, I need to pause here and acknowledge something important about William Thomson, Lord Kelvin, because his contributions run parallel to Clausius's and are deeply intertwined with this story. Thomson, the young Scotsman who had searched the Parisian bookstalls for Carnot's book, was one of the first people to synthesize Carnot's ideas about heat engines with Joule's ideas about the mechanical equivalent of heat. And he made a contribution that's directly relevant to our story about temperature. Thomson realized that Carnot's analysis implied something radical about temperature itself. If the efficiency of a perfect heat engine depends only on the temperatures of the hot and cold reservoirs, then temperature isn't just a number on a thermometer. It's a fundamental physical quantity with an absolute meaning. And in particular, there must be an absolute zero of temperature, a point below which you cannot go, a point where no more heat can be extracted from a substance. This idea had actually been glimpsed much earlier, around 1700, by a French physicist named Guillaume Amonton. Amonton had noticed that when you cool a gas, its pressure drops, and he'd had the thought, what would happen if you kept cooling it? If you plotted pressure against temperature, you got a straight line sloping downward, and if you extended that line, it hit zero pressure at a particular temperature. That temperature, Amonton speculated, might be the absolute bottom, the coldest anything could ever be. Amonton didn't calculate the number precisely, but later scientists did, and the answer turned out to be about minus 460 degrees Fahrenheit, or minus 273 Celsius. Thomson, in 1848, proposed a new temperature scale based on this absolute zero. On his scale, which we now call the Kelvin scale, zero is the coldest possible temperature. Water freezes at 273 Kelvin. Water boils at 373. Your body temperature right now is about 310 Kelvin, which is 98.6 Fahrenheit, a number you probably know by heart. The beauty of the Kelvin scale is that it gives temperature a physical meaning beyond just the reading on a thermometer. Temperature, measured in kelvins, is directly proportional to the average energy of the molecules in a substance. At absolute zero, all thermal motion stops. The molecules are as still as they can possibly be. As you go up in temperature, the molecules move faster and faster, vibrating and bouncing and spinning with more and more energy. Temperature is motion. Heat is energy. Thomson's absolute temperature scale would prove essential for the precise mathematical formulation of thermodynamics. But it also pointed, implicitly, toward the answer to a question that Clausius's mathematics had raised but not answered. What was entropy, really? Not just mathematically, but physically. What was actually happening at the deepest level when entropy increased? Clausius had given entropy a name, a formula, a set of mathematical properties. He had shown that it always increases, but he hadn't explained why. He hadn't said what it was in terms of the underlying mechanics of matter. For that, you needed someone willing to imagine a world that nobody could see. A world of atoms.
And here I want to step back from the mathematics for a moment, because what Clausius had revealed has a quality that goes beyond equations. The second law of thermodynamics is, in a very real sense, the law that gives time its direction. Think about it. The fundamental laws of physics, Newton's laws of motion, Maxwell's equations of electromagnetism, even the equations of quantum mechanics, are all time reversible. If you film a collision between two billiard balls and play the film backward, the reversed collision obeys Newton's laws just as perfectly as the forward one. There's nothing in the equations that tells you which direction is forward. The laws of physics work the same way in both directions of time. And yet, our experience of time is profoundly directional. We remember the past, but not the future. Eggs break but don't unbreak. People grow old, but not young. Everything around us seems to flow in one direction, from the past toward the future, and we never see that flow reverse. The second law of thermodynamics is the only law in fundamental physics that has this directionality built into it. Entropy increases toward the future. It was lower in the past. The direction of increasing entropy is the direction we call forward in time. This is why some physicists have called entropy the arrow of time. It's the thing that distinguishes the past from the future. Without it, the equations of physics would be perfectly happy running backward, and we'd have no way to tell which direction was which. Clausius glimpsed this, at least dimly. When he wrote that the entropy of the universe tends toward a maximum, he was describing a process that unfolds in time, that has a direction, that gives history its irreversible, unrepeatable quality. The universe started in a state of low entropy, high order, concentrated energy, and it has been moving ever since toward higher entropy, greater disorder, more dispersed energy. Everything that happens, every event, every process, every life, is part of this great unfolding. We are the universe's way of increasing its entropy, one breath, one heartbeat, one thought at a time. But Clausius couldn't explain why. He had identified the pattern, he had written the equation, he had named the quantity, but the mechanism, the deep reason why entropy always increases, remained hidden. It was as if he had discovered a river flowing inevitably toward the sea, but couldn't explain what gravity was or why water flows downhill. The man who would provide that explanation, who would look beneath the macroscopic surface of thermodynamics and see the churning, jostling, probabilistic world of atoms underneath, was already alive when Clausius published his work.
He was a young man in Vienna, passionate about music and mathematics in roughly equal measure. And he was about to take the deepest dive into the nature of matter that any human being had ever attempted. Before we get to Boltzmann, I want to take a step back and talk about atoms, because the story of heat and the story of atoms are inseparable, and you can't understand one without understanding the other. The idea that matter is made of tiny, indivisible particles is ancient. Democritus, a Greek philosopher writing around 400 BC, proposed that if you kept cutting matter into smaller and smaller pieces, you'd eventually reach something that couldn't be cut any further. He called these fundamental bits atomos, which simply means uncuttable. It was a beautiful idea, but for over 2,000 years it remained purely philosophical. Nobody could prove that atoms existed. Nobody could see them. Nobody could measure them.
By the early 1800s, the evidence was starting to accumulate. John Dalton, working in Manchester, the same city where Joule would later conduct his experiments, showed that chemical elements combine in fixed whole number ratios. 1 atom of this to 2 atoms of that. The simplest explanation was that matter really did come in discrete packets. The chemists were on board, more or less, using atoms as a working concept to organize their understanding of chemical reactions. But the physicists were more cautious, and with good reason, because saying that atoms exist as a useful concept for understanding chemistry is very different from saying that atoms are real physical objects that move and bounce and collide according to the laws of mechanics. The first claim is modest, the second is enormous. And it's the second claim that the story of heat requires, because if atoms are real, and if they move, then something immediately follows. Heat is motion. If a gas is made of tiny particles bouncing around, then a hot gas is one where the particles are bouncing fast, and a cold gas is one where they're bouncing slowly. Temperature is just a measure of how fast the particles are moving, on average, and heat flow is just the transfer of this motion from one group of particles to another. The fast-moving particles of a hot object bump into the slower-moving particles of a cold object and transfer some of their energy, the same way a fast billiard ball transfers energy to a slow one when they collide. The hot object slows down and cools, the cold object speeds up and warms, until eventually they're all moving at roughly the same speed and the temperatures equalize. This picture, which we now call the kinetic theory of heat, is so simple, so intuitive, and so correct that it's hard to imagine anyone resisting it. But resist it they did, fiercely, for decades. And the man who fought the hardest to establish the kinetic theory, who saw further into the atomic world than anyone else of his generation, who gave us the deepest explanation of entropy and the second law, was Ludwig Boltzmann. Boltzmann was born in Vienna in 1844 into a world of scientific and cultural certainty. The Austrian Empire was orderly, hierarchical, sure of itself. Science was built on firm foundations, the laws of Newton, the equations of Maxwell, the precisely measured quantities of experimental physics. Certainty was prized, speculation was distrusted, and Boltzmann was about to spend his entire career speculating about things nobody could see. He was not, by any account, a conventional figure. He was physically large, with poor eyesight that required thick glasses. He was intellectually restless, moving from one university to another throughout his career. Vienna, Graz, Munich, Leipzig, back to Vienna. He was emotionally volatile, swinging between periods of intense creative excitement and terrible, crushing depression. He loved music, particularly Beethoven and Wagner, and could lose himself at the piano for hours. He could also lose himself in mathematics for days at a time, emerging from deep calculations with insights that left his colleagues baffled. And he was guided, throughout his life, by 2 deep convictions. The first was that atoms were real. Not a convenient fiction, not a useful calculating device. Real, physical objects, as real as tables and chairs, just much, much smaller. The second was that the behavior of vast numbers of atoms could be described not by tracking each individual particle, which would be impossible, but by using the mathematics of probability. This second conviction was Boltzmann's great intellectual leap. And to appreciate it, you need to understand the scale of the problem. A single tiny cube of air, about the size of a sugar cube, contains roughly 27 billion molecules. That number is so large it's almost meaningless. 27 followed by 18 zeros. Each of those molecules is moving at over 1,000 miles per hour, constantly colliding with its neighbors, changing direction, changing speed, bouncing off the walls of whatever container holds the gas. Every single second, each molecule undergoes billions of collisions. The total number of collisions happening in that tiny sugar cube of air every second is a number so staggeringly large that writing it down would fill pages. Nobody can track all that. Nobody can write equations for each individual molecule and solve them simultaneously. The problem is not just difficult, it is, in the most literal sense, impossible. There are more unknowns than there are particles in the observable universe to count them with. But Boltzmann saw a way through.
He realized that you didn't need to track individual molecules. You needed to describe the statistical distribution of their properties. You didn't need to know exactly how fast each molecule was going. You just needed to know what fraction of the molecules were going at each speed. Think about it this way. You don't need to know the height of every person in New York City to say something meaningful about the population. You just need the distribution, the bell curve, showing how many people are short, how many are average, how many are tall. The individual details wash out. The statistical pattern emerges. James Clerk Maxwell, the great Scottish physicist, had already taken the first step in this direction. In 1860, Maxwell had derived a formula describing how the speeds of gas molecules should be distributed at a given temperature. At any temperature, most molecules are traveling at speeds near the average. But some are going much faster, and some much slower.
Maxwell's distribution gave the exact shape of this spread, and it was confirmed beautifully by experiments. But Maxwell had derived his distribution using a somewhat ad hoc argument. Boltzmann took it much further. Over the course of the 1860s and 70s, Boltzmann developed a comprehensive framework, now called statistical mechanics, for connecting the microscopic world of atoms to the macroscopic world of thermodynamics. He showed that temperature, pressure, volume, heat capacity, all the quantities that thermodynamics dealt with, could be derived from the statistical behavior of vast numbers of atoms. Temperature, for instance, is just the average kinetic energy of the molecules. If you take all the molecules in a gas, calculate the kinetic energy of each one, half times mass times velocity squared, and average them all together, you get a number that is directly proportional to the temperature as measured by a thermometer. That's all temperature is, an average. A statistical quantity describing the collective behavior of trillions of particles. And this is where Boltzmann's deepest insight came. Because once you think of matter as a collection of enormous numbers of particles whose behavior is described by probability, you can finally explain what entropy is and why it always increases. Imagine a simple example. You have a box divided into two halves by a removable partition. On the left side, you have a gas. On the right side, nothing, a vacuum. Now remove the partition. What happens? The gas rushes into the empty side and fills the whole box. Obviously. You've seen this happen 1,000 times with perfume, with cooking smells, with any gas released into a room. It expands to fill the available space. But why? Why doesn't the gas stay on one side? There's no force pushing it to the right, the molecules are just bouncing around randomly. The answer is purely statistical.
There are vastly, inconceivably more ways for the molecules to be spread evenly throughout the whole box than there are for them all to be crammed into just one half. Each individual molecule can be anywhere in the box with equal probability. But when you have trillions of molecules, the overwhelming likelihood is that they'll be roughly evenly distributed, simply because there are so many more arrangements that correspond to an even distribution than to a lopsided one. Boltzmann made this precise. He defined entropy in terms of the number of microscopic arrangements, what he called complexions, and what we now call microstates, that correspond to a given macroscopic state. A macroscopic state is what you can observe and measure: the temperature, the pressure, the volume. A microstate is the exact position and velocity of every single molecule. For any given macroscopic state, there are typically an astronomically large number of microstates that would look the same from the outside.
A gas evenly distributed in a box has an enormous number of microstates. Each molecule can be anywhere, going in any direction, and as long as the overall distribution is roughly uniform, the gas looks the same. But a gas compressed into just one half of the box has far fewer microstates. The molecules are restricted to a smaller volume. There are fewer positions they can occupy. Entropy, Boltzmann said, is proportional to the logarithm of the number of microstates. More microstates means higher entropy. Fewer microstates means lower entropy. And since a system, left to itself, will naturally evolve toward the state with the most microstates, simply because that's the most probable state, entropy will naturally increase. This is Boltzmann's famous equation, S equals K times the logarithm of W. S is entropy, W is the number of microstates, and K is a constant, now called Boltzmann's constant, that bridges the microscopic world of atoms to the macroscopic world of thermodynamics. That equation is carved on Boltzmann's tombstone in Vienna. It is his enduring legacy. And it explains, once and for all, what entropy is and why it always increases. Entropy increases because the universe moves toward the most probable state. Order dissolves into disorder, not because there's a force pushing it, but because there are so many more ways to be disordered than to be ordered. A dropped glass can shatter into 1,000 pieces because there are trillions of ways for the pieces to be scattered on the floor, but only one way for them to be assembled into a glass. The math is not subtle. The numbers are not close. The disordered states outnumber the ordered states by factors so large that the probability of spontaneously going from disorder to order is, for all practical purposes, 0. And this, finally, is the real reason your cup of tea cools down. The heat energy in the tea is concentrated in a small number of rapidly moving molecules. As those molecules bump into the slower molecules of the surrounding air, they share their energy. The energy disperses, spreads out over a larger number of molecules. The system moves from a less probable state, energy concentrated, to a more probable state, energy dispersed. Entropy increases. The tea cools, the room warms. And the process is irreversible, not because of any fundamental physical law forbidding the reverse, but because the reverse is so staggeringly improbable that you would have to wait longer than the age of the universe to see it happen by chance. This was the answer that Clausius had been groping toward, but could never fully express. Clausius had given entropy a name and a mathematical formula, but he treated it as a mysterious property of macroscopic systems. Boltzmann showed that it was a consequence of the statistics of the microscopic world. The second law of thermodynamics isn't really a law at all, in the same way that Newton's laws of motion are laws. It's a statistical truth. It says that overwhelmingly probable things happen, and overwhelmingly improbable things don't. Which is, when you think about it, the most obvious statement in the world, and also one of the most profound. Now, you might imagine that Boltzmann's ideas were greeted with enthusiasm. He had, after all, solved one of the deepest puzzles in physics. He had explained what entropy really was. He had connected the macroscopic world of temperature and heat to the microscopic world of atoms and probability. He had shown why the second law of thermodynamics works. Surely this would be recognized immediately as one of the great achievements of 19th century science. It was not. It was attacked, ridiculed, and rejected by some of the most eminent physicists of the era. And the ferocity of the opposition nearly destroyed Boltzmann, both intellectually and personally. The problem was atoms. Boltzmann's entire framework rested on the assumption that matter was composed of real, physical atoms moving according to the laws of mechanics. And in the late 19th century, there was a powerful faction within the physics community that refused to accept this. The leader of the opposition was Ernst Mach, the same Mach whose name you know from the Mach number used to measure the speed of sound. Mach was an Austrian physicist and philosopher of enormous prestige, a man whose opinions carried the weight of a pronouncement from on high. And Mach was an empiricist of the most uncompromising kind. He believed that science should deal only with what can be directly observed and measured. Since nobody had ever seen an atom, since no instrument of the era could detect one, Mach argued that atoms were a fiction, a mathematical convenience, a label that didn't correspond to anything real.
He famously stood up after one of Boltzmann's lectures in Vienna and said simply, "I don't believe that atoms exist." Imagine how that felt. You've spent your career building a mathematical framework of extraordinary power and beauty, a framework that explains thermodynamics from first principles, that gives entropy a physical meaning, that connects heat and temperature to the motion of particles. And one of the most respected physicists in your country stands up in a public lecture and dismisses the foundation of your life's work as a fantasy. Mach wasn't alone. Wilhelm Ostwald, a brilliant German chemist who would later win the Nobel Prize, was equally hostile. Ostwald led a school of thought called energetics, which held that energy, not atoms, was the fundamental reality. According to the energeticists, everything in physics could and should be described in terms of energy transformations, without any reference to hypothetical particles that nobody could see or measure. Atoms, in their view, were not just unproven, they were unnecessary. The concept of energy was all you needed. The energeticists had a point, or at least a reasonable argument. By the late 19th century, thermodynamics had been enormously successful as a macroscopic theory. You could predict the behavior of engines, gases, chemical reactions, and phase transitions without ever mentioning atoms. The equations of thermodynamics worked perfectly well as descriptions of macroscopic quantities: temperature, pressure, volume, entropy. Why complicate things by invoking invisible particles? Boltzmann's response was to argue, with increasing desperation, that the atomic hypothesis wasn't just a convenient fiction. It was the only way to explain certain phenomena, like the statistical nature of the second law, like the distribution of molecular speeds in a gas, like the specific heats of gases at different temperatures. The atoms were doing real work in the theory. They weren't decorative, they were essential. But the debates were brutal. At a meeting of the German Natural Scientists and Physicians Association in Lübeck in 1895, Boltzmann confronted Ostwald and the energeticists in a heated public debate. By most accounts, Boltzmann held his own intellectually, but the experience left him shaken. He felt isolated, embattled, fighting a war on multiple fronts against adversaries who controlled the most prestigious journals and academic appointments. And the attacks came not just from the energeticists. There were also mathematical objections to Boltzmann's statistical approach. The most famous was the reversibility objection, raised by Boltzmann's own colleague, Joseph Loschmidt. Loschmidt pointed out that the fundamental laws of mechanics are time reversible. If you film a collision between two molecules and play the film backward, the reversed collision also obeys Newton's laws perfectly. There's nothing in the microscopic laws of motion that distinguishes the forward direction of time from the backward direction. So how can Boltzmann derive an irreversible law, the second law, from reversible underlying mechanics? This was a genuinely deep objection, and Boltzmann took it very seriously. His answer was subtle and, at the time, deeply counterintuitive. He argued that the second law is not absolutely true in the same way that Newton's laws are true. It is overwhelmingly probable, but not certain. In principle, a gas could spontaneously compress itself into one corner of its container, just as a shattered glass could spontaneously reassemble itself. There's no law of physics forbidding it. It's just so stupendously unlikely that you would have to wait for a time period
vastly exceeding the age of the universe to see it happen. This argument, which is now universally accepted, was deeply unsettling in the 1890s. The idea that a fundamental law of physics was merely statistical, merely probable, rather than absolutely certain, seemed to undermine the deterministic worldview that had been the bedrock of physics since Newton. If the second law could, in principle, be violated, was it really a law at all? For Boltzmann, who believed passionately in the power of mathematics to describe reality, the rejection of his ideas was agonizing. He wrote, with visible pain, about the hostility he faced. He described himself as a man swimming against the current. He compared himself to an old dog who could still learn new tricks, but whose audience had lost patience. Throughout his life, Boltzmann had suffered from severe bouts of depression. Some of these episodes were triggered by the scientific controversies, but others seemed to come from nowhere, descending on him without warning and leaving him unable to work, unable to think, unable to function.
In the language of our time, he would likely be diagnosed with bipolar disorder. In his own time, he simply suffered. By the early 1900s, Boltzmann's health was deteriorating. His eyesight was failing. His depressions were becoming more frequent and more severe. He had taken a professorship in Vienna, which should have been a triumphant homecoming, but the atmosphere was toxic. Mach, though retired, still cast a long shadow. The energeticist arguments still swirled in the journals, and Boltzmann felt that his life's work, the atomic theory and the statistical interpretation of entropy, was being rejected by the very community that should have celebrated it. In September 1906, Boltzmann and his family went on holiday to the coastal town of Duino, near Trieste, on the Adriatic Sea. It should have been a rest, a chance to recover, a break from the pressures of academic life.
On September 5th, while his wife and daughter were down at the beach, Boltzmann hanged himself in the room where they were staying. He was 62 years old. The tragedy of Boltzmann's death is compounded by what happened in the years immediately following. Within just a few years of his suicide, the evidence for atoms became overwhelming. In 1905, the year before Boltzmann died, Albert Einstein published a paper on Brownian motion, the random jiggling of tiny particles suspended in a liquid, showing that this motion could be explained quantitatively by the bombardment of invisible atoms. In 1908, Jean Perrin confirmed Einstein's predictions experimentally, providing evidence so compelling that even the most stubborn skeptics had to concede. Atoms were real.
The man who had fought the hardest for atoms, who had endured decades of ridicule and opposition, who had built the mathematical framework that proved atoms could explain the macroscopic world, did not live to see his vindication. He died believing, or at least fearing, that his life's work had been in vain. And within a generation, his ideas would be recognized as some of the most profound and important in the history of physics. Today, if you visit the Zentralfriedhof, the Central Cemetery in Vienna, you can find Boltzmann's grave. It's a handsome monument, white marble, with a bust of Boltzmann looking out at you, with an expression that might be serenity, or might be sadness, depending on the light. And carved into the stone above the bust, in large, clear letters, is the equation. S equals K log W. That's all it says. No words of praise, no biography, no list of accomplishments. Just the equation. The formula that explains what entropy is, what the second law means, why your cup of tea cools down, why the universe is winding down, why time seems to flow in one direction. The answer to one of the deepest questions in all of physics, reduced to 5 characters carved in stone. I want to say a bit more about why the atomic theory was so controversial, because from our modern vantage point, it can be hard to understand why brilliant scientists would resist such an obviously correct idea. But if you put yourself in the shoes of a late 19th century physicist, the resistance makes more sense than you might think. The fundamental problem was that nobody had ever seen an atom. In the 1880s and 90s, no microscope could resolve anything close to atomic scales. The smallest things visible under the best optical microscopes were bacteria, which are roughly 1,000 times larger than a typical atom. Atoms were far, far below the threshold of observation.
They were inferred from indirect evidence, the fixed ratios of chemical reactions, the behavior of gases, the patterns in spectroscopic data. All of this evidence was consistent with the existence of atoms, but none of it constituted direct proof. And this mattered, because the late 19th century was a time of intense philosophical debate about what counted as legitimate scientific knowledge. The positivists, led by thinkers like Ernst Mach, argued that science should concern itself only with observable phenomena, with things that could be directly measured and verified. Atoms, by this standard, were not legitimate scientific objects. They were hypothetical entities, useful fictions, shorthand for patterns in experimental data. To claim that atoms were real, that they existed as physical objects occupying specific positions in space and moving with specific velocities, was to go beyond the evidence, to make a metaphysical claim that science had no business making.
This wasn't stupid. It was a principled position, motivated by a genuine concern about the foundations of scientific knowledge. Mach had seen theories come and go. He had seen confident claims about the nature of reality turn out to be wrong. He was determined to anchor science in what could actually be observed, and atoms could not be observed. From his perspective, Boltzmann's statistical mechanics was an elaborate mathematical fantasy, a theory about imaginary objects that might or might not correspond to anything in the real world. Boltzmann's response to this critique was both emotional and intellectual. On the intellectual side, he argued that the atomic hypothesis wasn't just a convenient fiction. It was necessary. Without atoms, you couldn't explain the statistical nature of the second law. Without atoms, you couldn't derive the distribution of molecular speeds in a gas.
Without atoms, you couldn't account for the specific heats of gases, which depended on the number of ways atoms could move and vibrate. The atoms were doing real explanatory work that couldn't be replicated by any purely macroscopic theory. On the emotional side, Boltzmann took the attacks personally. He felt that his life's work was being dismissed, that the mathematical framework he'd spent decades building was being treated as worthless. He wrote anguished letters and gave impassioned lectures. He compared himself to various historical figures who had been persecuted for their ideas, which didn't always endear him to his colleagues, but which reflects the depth of his conviction. The debate between Boltzmann and the energeticists wasn't just about atoms. It was about the nature of scientific explanation itself. What does it mean to explain something?
Is it enough to describe the mathematical relationships between observable quantities? Or do you need to provide a physical mechanism, a picture of what's happening at the deepest level? Mach said the former. Boltzmann said the latter. And in the end, Boltzmann was right, though he didn't live to see it proven conclusively. The proof came, as I mentioned, from Brownian motion. In 1827, the Scottish botanist Robert Brown had observed that tiny pollen grains suspended in water jiggled around randomly, as if buffeted by invisible forces. Nobody could explain this for decades. In 1905, Einstein published a paper showing that if water was made of atoms, the random thermal motion of those atoms would push the pollen grains around in exactly the pattern Brown had observed. Einstein derived precise,
quantitative predictions for the statistical properties of the jiggling, predictions that depended on the size and number of atoms.
In 1908, the French physicist Jean Perrin confirmed Einstein's predictions experimentally. He tracked the motion of tiny suspended particles under a microscope and showed that their behavior matched Einstein's atomic theory with extraordinary precision. From his measurements, Perrin could even calculate Avogadro's number, the number of atoms in a mole of substance, and the value agreed with estimates from completely independent methods. After Perrin's experiments, the debate was essentially over. Even Ostwald, Boltzmann's most vocal opponent, conceded that the evidence for atoms was now overwhelming. In a remarkable statement, Ostwald wrote that he had been convinced by the quantitative agreement between theory and experiment regarding Brownian motion. Atoms were real. But Boltzmann, by then, had been dead for 2 years. He had gone to his grave not knowing whether his life's work would be accepted or forgotten. In the end, it was not just accepted, it became the foundation of modern physics. Statistical mechanics, the framework Boltzmann built, is now one of the pillars on which quantum mechanics, solid-state physics, cosmology, and information theory all rest. His equation, S equals K log W, is one of the most important equations in all of science, alongside Einstein's E equals mc squared and Newton's F equals ma. The tombstone in Vienna tells the whole story. 5 characters, the work of a lifetime, the answer to a question that consumed him, and a vindication that came just a few years too late. So what happened to the caloric theory? How did it actually die? This is a question worth spending some time with, because the answer reveals something important about how science really works. Something that doesn't quite match the tidy stories you read in textbooks. The caloric theory didn't die the way theories are supposed to die. There was no single experiment that definitively refuted it.
There was no dramatic moment when the scientist stood up and said, "Look, here is the proof that caloric is wrong," and everyone nodded and moved on. The death of caloric was slow, messy, and ambiguous, and it happened in stages over about a century. Rumford's cannon experiment in 1798 was the first serious blow, but the caloric theorists weathered it. They argued that the heat generated by friction could be explained by changes in the heat capacity of the metal, that the caloric was already there and was simply being rearranged. Their argument wasn't crazy. It was wrong, but it wasn't crazy. Joule's experiments in the 1840s were a much heavier blow. The mechanical equivalent of heat, the precise and reproducible conversion of work into heat, was very difficult to explain if heat was a conserved substance. Where was the caloric coming from when you churned water with a paddle? The falling weights didn't contain caloric. The paddle didn't contain caloric.
Heat was being created from mechanical motion, and you could measure the exchange rate with extraordinary precision. This was deeply problematic for the caloric theory. But even Joule's work didn't kill caloric instantly. Some scientists argued that the heat generated by friction came from the surroundings, drawn in by the mechanical action. Others simply ignored Joule's results. When he first presented his findings at a meeting of the British Association for the Advancement of Science in 1843, the audience was largely indifferent. His paper was received politely, but without enthusiasm, and the chairman suggested he summarize his conclusions quickly because they were running behind schedule. What ultimately killed caloric was not a refutation, but a replacement. The kinetic theory of heat, the idea that heat is the motion of atoms, didn't just explain everything caloric explained, it explained more. It explained things caloric couldn't touch. Caloric could explain why hot things expand and why heat flows from hot to cold. But it couldn't explain, in any satisfying way, why friction generates unlimited heat, or why the specific heats of gases have the values they do, or why the second law of thermodynamics is true, or what entropy actually is. The kinetic theory could. It explained all of these things, and it did so from a single, unified picture. Matter is made of particles in motion, and all the macroscopic properties of heat and temperature are consequences of that motion. This is an important lesson about how scientific theories change. We tend to think of science as a series of dramatic confrontations, crucial experiments that prove one theory right and another wrong. And sometimes that happens. But more often, theories die not because they're refuted, but because they're superseded. A better theory comes along, one that explains everything the old theory explained and more. And the old theory simply becomes unnecessary. It withers away from neglect, not from attack. Peter Atkins, in his book on the laws of thermodynamics, makes a beautiful point about this. He argues that thermodynamics, the science of heat and energy, is unusual in the history of physics because it was developed backward. Most branches of physics start with microscopic mechanisms and build up to macroscopic predictions. You start with atoms and derive the behavior of gases. You start with electrons and derive the properties of circuits. But thermodynamics went the other way. The laws of thermodynamics were discovered empirically through the study of steam engines and heat flow and chemical reactions, without any reference to atoms at all. They were macroscopic laws, describing the behavior of bulk matter. Only later, with Boltzmann's statistical mechanics, was the microscopic foundation laid. This backward development is part of why the caloric theory survived so long. You could do thermodynamics perfectly well without knowing what heat was made of. The laws worked regardless. Carnot's analysis of heat engines gave correct predictions whether you believed heat was a substance or a form of motion. Clausius's entropy calculations worked just as well with caloric as with kinetic theory. The macroscopic framework was robust, and it didn't care about the underlying mechanism. And that's actually a remarkable thing. It means that the laws of thermodynamics are, in a sense, deeper than the atomic theory. They don't depend on the specific details of what matter is made of. They would be true even if atoms were different from what they are. They would be true even if matter were continuous rather than particulate, as long as there are enough degrees of freedom for statistics to apply. The laws of thermodynamics are among the most universal statements in all of science, and their universality comes precisely from the fact that they were discovered independently of any particular model of matter. This is why Carnot, working within the caloric framework, could derive correct results about the efficiency of heat engines. The deeper truth he'd discovered about the relationship between temperature differences and the ability to do work was robust enough to survive the death of the theory that had given birth to it. And this is why Clausius's entropy, defined in purely macroscopic terms, turned out to be exactly the same quantity that Boltzmann later derived from atomic statistics. The macroscopic and microscopic descriptions agree because they're both describing the same underlying reality, just from different vantage points. So the caloric theory died, but its legacy lived on. Not the theory itself, not the idea that heat is a substance, but the mathematical structures and physical insights that had been developed within it. Carnot's cycle, Clausius's entropy, the laws of thermodynamics, all these survived the transition from caloric to kinetic theory essentially unchanged. The framework held.
Only the interpretation shifted. And that, I think, is the real moral of this story. The caloric theory wasn't just a mistake. It was a productive mistake. It was a scaffolding that supported the construction of something true and lasting. And when the construction was complete, the scaffolding was removed and the building stood on its own. We don't need caloric anymore, but we wouldn't be where we are without it. Now let me take you one step further, because the story of heat doesn't end with Boltzmann's equation and the death of caloric.
The understanding that heat is the motion of atoms has consequences that reach far beyond the world of steam engines and thermometers. It reshapes our understanding of, well, everything. Consider what it means for the concept of temperature itself. Temperature, we now know, is the average kinetic energy of the molecules in a substance. But average is doing a lot of work in that sentence. In any gas at any temperature, the molecules are not all moving at the same speed. Some are fast, some are slow, and most are somewhere in between. The distribution of speeds follows Maxwell's curve, a smooth, bell-shaped distribution that shifts to higher speeds as the temperature increases. At room temperature, the molecules of nitrogen in the air around you right now are moving at an average speed of about 1,100 miles per hour, faster than a rifle bullet. But some molecules in that same air are barely crawling, and a few are going twice or 3 times the average.
They're all mixed together, fast and slow, jostling and colliding, exchanging energy with every impact. And here's something that might surprise you. The temperature of a single molecule is a meaningless concept. Temperature only makes sense when you're talking about large collections of molecules. It's a statistical quantity, like the average height of a population. Asking what the temperature of one molecule is would be like asking what the average height of one person is. The question doesn't quite make sense. Temperature emerges from the collective behavior of vast numbers of particles. It's a property of the crowd, not the individual. This means that temperature, this thing we measure every day, this thing we feel in our bones, this thing that seems so real and immediate, is actually an abstraction. It's a summary, a shorthand for the kinetic energy distribution of trillions of particles that are individually invisible.
You feel warmth, not because warmth is a thing that exists out there in the world, but because the molecules hitting your skin are doing so with a certain average energy, and your nerve endings have evolved to detect that average. What you experience as a sensation of heat is, at the deepest level, the statistical effect of enormous numbers of molecular collisions. This perspective, which we owe ultimately to Boltzmann and his statistical mechanics, transforms our understanding of the physical world. Everything you see around you, everything you touch and feel and taste, is an emergent property of the behavior of unimaginably large numbers of particles, each individually too small to see, collectively producing the rich, textured, sensory world you inhabit. The solidity of the chair you're sitting in is an emergent property of electromagnetic forces between atoms. The color of the sky is an emergent property of photons scattering off molecules of nitrogen and oxygen.
The warmth of your own body is an emergent property of trillions of chemical reactions, each one releasing a tiny amount of energy, collectively maintaining your internal temperature at a steady 310 Kelvin. And the second law of thermodynamics, that inexorable tendency of entropy to increase, governs it all. Every process that happens in your body, every beat of your heart, every breath, every thought, every movement of every muscle, increases the total entropy of the universe. Your body takes in concentrated chemical energy in the form of food, uses a tiny fraction of it to maintain its internal order, and dumps the rest into the environment as waste heat, dispersed, spread out, irreversibly degraded. You are, from the point of view of thermodynamics, a temporary local decrease in entropy, sustained by a constant throughput of energy from concentrated to dispersed. You are a structure that exists only because it can tap into the great cosmic flow, from order to disorder, siphoning off a tiny fraction of the energy to maintain itself, like a whirlpool in a stream. The whirlpool persists as long as the water flows. When the flow stops, the whirlpool disappears. Peter Atkins captures this with a beautiful analogy. The universe is like a waterfall, rushing from order to disorder, and living things are like the spray thrown up by the falling water. We are temporary structures, intricate and beautiful, sustained by the very process that will eventually destroy us. We exist because entropy is increasing, and we will cease to exist when it reaches its maximum, but that's a long, long way off. The universe has plenty of concentrated energy left to spend. Stars are still burning. Galaxies are still forming. Life is still evolving and spreading and finding new ways to harness the flow.
The second law guarantees that this will all end eventually, in the vast, cold, uniform emptiness of the heat death. But eventually is a very long time. Billions of years. Trillions, perhaps. We have time. So let me bring all of this together, because we've traveled a long way tonight, and I want you to see the arc of this story clearly before we're done. We started with a question that seems so simple a child might ask it. What is heat? And we traced humanity's attempts to answer that question across 2,500 years, from the ancient Greeks to the Victorian physicists to the statistical mechanics of the 20th century. The first real attempt at an answer came from Aristotle, who said heat was a fundamental quality of matter, one of the 4 basic properties that defined the elements. This idea lasted for nearly 2,000 years, not because it was correct, but because it was embedded in a larger philosophical system that made sense of the world. Then, in the 1600s, thinkers like Bacon and Boyle suggested that heat might be a form of motion, that the tiny particles making up matter were vibrating and jostling, and that heat was simply a measure of that activity. The idea was perceptive and, as it turned out, correct, but it was vague, it was unmathematical, and it couldn't compete with what came next. In the late 1700s, the caloric theory arrived. Lavoisier, the greatest chemist of his age, declared heat to be an element, a weightless fluid called caloric that flowed between the particles of matter. The theory was elegant, quantitative, and explanatory. It accounted for thermal expansion, latent heat, heat flow, and the behavior of gases. It was a beautiful, wrong answer, and it dominated science for over a century. Rumford attacked it with his cannon-boring experiments, showing that friction could produce unlimited heat from mechanical work alone. The theory absorbed the blow and survived. Carnot used it to analyze the fundamental operation of heat engines and derived correct results about efficiency and temperature, results that endure to this day. Even though the theory on which they were based was wrong, the wrong theory was so good that it produced right answers. Then Joule, working in his brewery cellar with his extraordinarily precise thermometers, proved that heat and mechanical work are interconvertible, that they are 2 forms of the same quantity we now call energy. This was the first law of thermodynamics, and it effectively killed the idea that heat was a conserved substance. But the caloric theory was so deeply embedded in scientific practice that even Joule's work didn't eliminate it overnight. Clausius took the next step, showing that heat flow has a direction, that energy always disperses from concentrated to diffuse, and that this tendency can be measured by a quantity he called entropy. The second law of thermodynamics said that entropy always increases, that the universe is winding down, spreading out, moving irreversibly toward a state of maximum disorder. But Clausius couldn't explain why. He named the phenomenon but didn't reveal its mechanism. And finally, Boltzmann, that passionate, tormented genius, showed what entropy really was. He demonstrated that the macroscopic world of heat and temperature was the statistical outcome of the microscopic world of atoms in motion. Entropy was a measure of probability, of the number of ways the microscopic particles could be arranged. The second law was true, not because of any fundamental force driving the universe toward disorder, but because disorder is overwhelmingly more probable than order. The universe doesn't have a tendency toward disorder. It just goes where the numbers point. And the numbers, the incomprehensibly vast numbers of possible molecular arrangements, point overwhelmingly toward dispersal, toward spreading out, toward the evening out of temperature differences. With Boltzmann's work, the caloric theory was finally, completely, irreversibly dead. Not because it had been refuted by a single experiment, but because something better had replaced it. The kinetic theory of heat, the picture of matter as atoms in motion, explained everything caloric had explained, and vastly more besides. The beautiful wrong answer was no longer needed. But its legacy persists, in ways you might not expect. Every time an engineer uses Carnot's efficiency formula, they're standing on insights that were born within the caloric framework. Every time a physicist writes down the entropy of a system using Clausius's equation, they're using a concept that was first articulated in caloric terms. The language of thermodynamics, the mathematical structures, the physical laws. All of these were developed during the era of caloric, and they survived the transition to the atomic picture essentially unchanged. That's the remarkable thing about the laws of thermodynamics. They don't care what heat is made of. They are true regardless of the underlying mechanism. They are so robust, so universal, that they could be discovered and formulated correctly, even within a fundamentally wrong theoretical framework. The zeroth law, that if two objects are each in thermal equilibrium with a third, they're in equilibrium with each other, is a statement about temperature that doesn't depend on whether temperature is a measure of caloric content or kinetic energy. The first law, that energy is conserved, is true whether you think of heat as a fluid or as molecular motion.
The second law, that entropy always increases, holds whether you define entropy in Clausius's macroscopic terms or Boltzmann's microscopic ones. The laws are deeper than any particular model of matter. Arthur Eddington, the great British astrophysicist, once said that if someone points out that your theory of the universe disagrees with Maxwell's equations, then so much the worse for Maxwell's equations. If it is found to be contradicted by observation, well, these experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. Eddington was being slightly tongue-in-cheek, but only slightly. The second law of thermodynamics is as close to an absolute truth as science gets. It governs everything: the evolution of stars, the chemistry of life, the functioning of your brain, the eventual fate of the cosmos.
And it was discovered by people who didn't even know what heat was. Think about that for a moment. The humans who uncovered the laws of thermodynamics were wrong about the most basic question you could ask. What is the thing they were studying? And yet they got the laws right. They found the truth in spite of their misunderstanding. They built a science of extraordinary power and universality on a foundation of error. And when the foundation was eventually corrected, the science remained standing. If there's a lesson in this, I think it's about humility. We like to think that science advances by replacing wrong ideas with right ones, that the truth marches forward in a straight line from ignorance to understanding. But the real story is messier than that. The real story is that wrong ideas can be productive. Beautiful mistakes can lead to genuine discoveries. Useful fictions can support real truths. And the line between what's right and what's wrong is sometimes much less clear than we'd like to believe. The caloric theory was wrong, but it was a magnificent kind of wrong. It was wrong in a way that helped science move forward. It was a ladder that humanity climbed on its way to understanding. And when we reached the top, we kicked the ladder away and stood on the understanding alone. We couldn't have gotten there without it. And now here you are, lying in the dark, and your body is doing the thing it's always doing. The thing it's been doing every second of every day of your life. It's radiating heat. The warmth of your metabolism, the energy released by the trillions of chemical reactions happening in your cells right now, is flowing outward, into the air, into the blankets, into the walls of the room. And what's happening at the deepest level is that the molecules in your skin, vibrating with the energy of life, are bumping into the cooler molecules of the air around you, transferring a little bit of their kinetic energy with each collision. Your body is a warm island in a cooler sea, and the heat is flowing outward, driven by nothing more than the statistics of molecular motion. The fast molecules slow down a little. The slow molecules speed up a little. Entropy increases, just slightly, just infinitesimally, with every exchange. This has been happening since the moment you were born. It will keep happening until the moment you die. And after that, it will continue as the heat that was your life disperses into the environment, spreading out, diluting, becoming part of the vast, gentle, ever-increasing background warmth of the universe. Francis Bacon said heat was motion back in 1620, and he was right, though he couldn't prove it.
Lavoisier said heat was a fluid in 1789, and he was wrong, though his error was glorious. Rumford showed that heat could be created from friction in unlimited quantities. Carnot showed that the flow of heat could do work, and that the efficiency of any engine was limited by the temperature difference between hot and cold. Joule proved that heat and work were two faces of the same coin. Clausius named the relentless dispersal of energy and called it entropy. Kelvin identified the absolute zero of temperature, the point where all thermal motion ceases. And Boltzmann, brilliant, emotional, tormented Boltzmann, showed what it all meant. He showed that temperature is the average energy of moving molecules. He showed that entropy is the logarithm of the number of ways those molecules can be arranged. He showed that the second law is not a decree from on high, but a statistical truth, the most probable outcome of the most enormous numbers in nature. He saw deeper into the nature of heat than any human being before him, and the world repaid him with ridicule and isolation. And he died believing his life's work had been rejected. His equation, S equals K log W, is carved on his tombstone. 5 characters that contain within them the explanation for why your tea gets cold, why your body radiates warmth, why stars burn out, why time seems to have a direction, why the universe, for all its beauty and complexity, is slowly, inevitably, gently winding down. But winding down doesn't mean dying. Not yet. Not for a very, very long time. Because right now, right here, in this tiny corner of the cosmos, the great unwinding is doing something beautiful. It's creating structure. It's creating complexity. It's creating you. Your body maintains itself at 98.6 degrees Fahrenheit, 310 Kelvin, a narrow, warm band of order in a cold and disordering universe. And it does this by consuming concentrated energy and dispersing it. Every breath you take brings in oxygen and exhales carbon dioxide and heat. Every heartbeat pumps warm blood through cooler tissues. Every thought fires neurons that release waste heat into your skull. You are an engine, a thermodynamic engine, just like Carnot's ideal cycle, converting concentrated energy into dispersed energy and using the proceeds to stay alive. The second law says you can't do this forever. It says that eventually the concentrated energy will run out, or the temperature differences will equalize, and the engine will stop. And on the scale of the universe, that's true. But on the scale of a human life, on the scale of this evening, on the scale of the next few hours while you sleep, the engine is running beautifully. Your heart is pumping. Your lungs are breathing. Your cells are metabolizing. The warmth is flowing, gently, quietly, from your body into the night. 200 years ago, they would have said caloric was streaming out of you. A century ago, they would have said your thermal energy was dissipating into the environment. Today, we say that the molecules in your skin are sharing their kinetic energy with the cooler molecules of the air, and the entropy of the universe is increasing by the tiniest possible amount. All three descriptions are pointing at the same thing, the same warmth leaving the same body on the same quiet night. The words have changed, the understanding has deepened, but the physics has been the same since the first human being lay down beside a dying fire and felt the cold creep in. And the people who figured all of this out, Bacon with his lists and his careful observations, Black with his meticulous calorimetry, Lavoisier with his elegant but ultimately wrong theory, Rumford with his canon and his impossible personal life, Carnot with his military humiliation and his slim, ignored masterwork, Joule with his brewery thermometers and his honeymoon waterfalls, Clausius with his equations and his cosmic pronouncements, Thomson with his absolute zero, Boltzmann with his atoms and his anguish. All of them were trying to answer the same simple question that you might ask tonight, lying here in the dark, feeling the warmth drain slowly from your fingertips. What is heat? And now you know. Heat is motion. The motion of atoms, of molecules, of the tiny, invisible, ceaselessly jostling particles that make up everything in the universe, including you. When you feel warmth, you're feeling those particles vibrating. When you feel cold, you're feeling them slow. When heat flows from your body into the night air, what's flowing isn't a substance, isn't a fluid, isn't a thing at all. What's flowing is energy, transferred from faster particles to slower ones, spreading out, dispersing, equalizing, in accordance with the most probable outcome of the most enormous numbers in nature. You are made of moving particles. Your warmth is their motion. And tonight, as you settle deeper into your pillow and let your thoughts grow quiet, those particles will keep moving, keep jostling, keep sharing their energy with the air around you. Your body will cool slightly as you sleep because your metabolism slows and generates less heat. But the motion never stops completely. As long as you're above absolute zero, and you are, your molecules are dancing.
They were dancing before you were born. They'll be dancing after you're gone. The dance is older than life, older than Earth, older than the stars. You don't need to understand all of it.
You don't need to hold on to any of it. The motion is happening without your permission, without your awareness, without any effort at all. Your body knows how to keep itself warm. It's been doing it every second of every day since you first drew breath. And it will keep doing it tonight, while you sleep, while your thoughts dissolve, while the warmth flows gently out of you and into the vast, patient, ever-cooling universe. Just let it flow. Let the entropy increase, just a little, just enough to let you rest. The molecules will take care of the rest. Breathe, and let yourself drift. The warmth is still there. The motion continues. And somewhere, on a headstone in Vienna, 5 characters carved in stone are quietly, beautifully, explaining why.